Hello wonderful person, this is Anton, and today we're going to discuss a very strange discovery of what seems to be a kind of a super kilonova. Basically, a never before seen explosion in outer space that definitely surprised everyone in astronomy. And specifically because we've never seen this before, this has never been anticipated or predicted, and seems to involve some kind of a very strange phenomenon that we're going to be discussing in this video. And so let's talk about this recent discovery and some of the studies behind this in a little bit more detail, and also discuss why this particular discovery is so important. But first, as always, you can find all of the studies related to this in the description below. But why was this so unusual, and why was this so bizarre? Well, here the problem is actually pretty simple. For decades, astronomers believed that we had pretty well-defined categories when it comes to various astronomical explosions. For example, we had things like nova, which involve white dwarfs, and we had supernova, which involves collapsing stars. But then in 2017, we also discovered something that was kind of predicted, but never officially observed. This was the first official confirmation that colliding neutron stars eventually produce a very specific type of an explosion referred to as a kilonova. The event that we now understand pretty well, and the event that's almost certainly responsible for the formation of a lot of complex elements, including gold and platinum, that we see all over the place. But in late 2025, the universe delivered an event that broke all of our expectations. A completely new type of an explosion that's a little bit bizarre and is currently just referred to as a super kilonova. Because in this case, the star exploded not just once, but twice. And that's basically the story of the event, whose name you see right here. But to appreciate the event, let's go through some of the differences between these explosions, just so that all of this makes sense. So first, let's talk about the supernova. The powerful luminous explosions that mark the final evolutionary stage of a typical massive star. And so when a star reaches a certain age, its core starts to collapse and produces a powerful explosion. This releases tremendous amount of energy, which then results in the formation of many different complex elements up to iron. And so, for example, things like carbon and silicon that's all over the place on planet Earth all came from various supernova. And these events are normally pretty bright. Their peak brightness is usually comparable to the entire galaxy. But they fade pretty quickly over several weeks, and after a few months are barely visible. And so here, a typical supernova is usually described as a kind of a death of a star, although technically it's really a transformation, because the star just becomes something else like a neutron star or a black hole. But obviously supernova are not something that's unusual today, and we see many of them every single year. Here's a really good example of a typical brightness curve for a supernova. In contrast, a kilonova is born from a completely different type of an event. This is a different type of cosmic violence involving the merger of two compact objects. Here this has to be either two neutron stars or a neutron star and a black hole. And normally this is a much shorter and a much fainter event, with the name kilonova literally coming from the fact that these events are usually 1/10 or maybe 1/100th the brightness of a typical supernova. But these events are still significant because of what they create. During this relatively brief period and during this chaotic merger, a massive neutron flux ends up producing even much heavier elements, even elements like uranium. This usually involves the process referred to as the R process. And so basically a lot of much heavier elements seem to form during kilonova and not supernova. And though at first their existence was only speculated, as I mentioned, it was definitively confirmed in 2017. The historic event that you see right here. And so this iconic kilonova was the first time scientists detected gravitational waves linked directly to actual optical emissions, which essentially confirmed that neutron-star collisions seem to produce kilonova. For scientists back then, this was a monumental discovery, and since then we actually have not seen anything similar yet. But that's until August of 2025, and specifically August 18th. Here, gravitational wave detectors LIGO, Virgo, and Kagra once again registered another bizarre signal, a signal indicating a compact binary merger. But crucially, around the same time, or almost exactly at the same time, the famous automated facility known as ZTF or Zwicky Transient Facility rapidly identified a burst of light that you can kind of see right here. And that's pretty much the same thing that happened in 2017. So here obviously a lot of astronomers were super excited because we might have just observed another kilonova linked to another gravitational wave event. And initially, for the first few days, it did indeed look exactly like this event from 2017. In essence, it faded pretty fast and produced a lot of very intense red glow, that once again suggested the presence of a lot of heavy elements like gold. And more importantly, gravitational waves and the optical event seem to be located in a relatively similar area of the sky. So here the correlation suggested that this was exactly the same event. But this is where the story got super bizarre. Following the first few days, the entire event changed completely. Unlike the previous detection here, it did not continue to fade and instead started to brighten again and again, eventually turning blue. But then it also started to display a lot of spectral features involving hydrogen and helium, which was completely unexpected and could not be explained through a kilonova explosion involving typical neutron stars. And so here this change suddenly made it look like a type 2b supernova, basically involving a young stripped envelope star, and not like a typical neutron star merger that we observed in 2017. And so what exactly was this? Was it neutron stars or a core collapse of a progenitor star without hydrogen layers? So here we had a completely new cosmic puzzle. And for the past few months, that's exactly what the scientists behind this recent study were trying to solve. They tried to figure out how a bizarre kilonova can then transform into a supernova just a couple of days later, which basically made them propose a new phenomenon, superkilonova. Yeah, not particularly original. I mean, if it was me naming it, I would have come up with something like double boom boom or something. But I guess for now we'll have to go with superkilonova. But that's not the only reason why this event is so bizarre and not the only strange observation. Because the strangest observation here is actually in what seems to have collided initially and the nature of this gravitational wave itself. Okay, let's briefly discuss neutron stars and black holes. So normally, a neutron star responsible for one of these kilonova is an incredibly dense remnant left behind after a core collapse supernova of a much older star. And while traditionally researchers always believed that a typical neutron star should have a mass of about 1.2 to maybe 3 solar masses in total, anything more than that becomes a black hole, anything less should be impossible. This is based on a lot of detailed simulations on how massive stars collapse and how they produce neutron stars. But the analysis of this gravitational wave currently suggests that one of these objects was less massive. Here the merger involved at least one neutron star that was actually even less massive than the Sun, a sub-solar mass object. But finding a neutron star below the threshold of 1.2 solar masses currently once again creates a bit of a problem. And that's because it creates a challenge for standard understanding of how massive stars evolve and how they go supernova. So even if it wasn't for the explosion, this was already kind of mysterious. And so this is why the scientists had to propose this new concept of double boom boom, superkilonova. Here the term describes a kind of a core collapse supernova that simultaneously involves an R-process nucleosynthesis, usually associated with a typical kilonova event. And so here the model suggests a very bizarre chain of events. First, it involves some kind of a massive, rapidly spinning star. And here obviously the star becomes unstable because it reaches the end of its life. And so the star explodes as a supernova. This is a core collapse event. But because the star is spinning so fast, the collapsing core actually undergoes a kind of a splitting event, or even forms a disk of material that fragments into pieces. And so this may even lead to the formation of a very large rotating accretion disk. And this fragmentation results in the formation of at least one, but possibly two, subsolar mass neutron stars. But neutron stars that are super close to each other and are moving in extremely tight orbits. And so almost right after their formation, these brand new baby neutron stars start to spiral toward each other and then eventually merge, creating the gravitational wave signal and the kilonova's characteristic red glow. So essentially resulting in this double detonation. And so in this scenario, the supernova blast expands rapidly, overwhelming and obscuring the light from the smaller, fainter kilonova merger that happened inside of it. Which explains why the event at first looked like a kilonova, but later started to brighten and shifted color to resemble a typical core collapse supernova. And all of this was just a result of a large, fast-spinning star. And if this hypothesis is confirmed, it basically presents us with a completely new stellar evolutionary pathway, physically capable of creating these very bizarre subsolar neutron stars we actually never knew could be possible. And it obviously reveals that the universe is way more complex and can create additional objects we never expected. However, the team behind the study emphasizes one important fact. The gravitational wave signal and the light coming from this particular galaxy still has a slight chance to be completely unrelated. Or basically, just to rephrase this, there is still about 2 to 4% chance that this is a completely accidental alignment and the gravitational waves, along with the kilonova and supernova explosions, are maybe just completely separate events. And so to resolve this mystery, researchers are going to have to try to find additional similar events in the future, and will hopefully have additional telescopes observing them and analyzing the details. Especially because even in this observation, some things still don't make sense. For example, during a kilonova event, we expect to see certain X-ray emissions and radio emissions, which were not observed here. And so if this involved two neutron stars colliding, why was there no X-rays or radio emissions? Additionally, scientists discovered hydrogen moving at approximately 17,000 km per second, which seems to actually suggest that this was a Type II supernova, but the changes in color from red to blue made no sense. Either way though, this is definitely one of the more important scientific discoveries in 2025, because we've just never seen anything like this anywhere. Here, this definitely opens our eyes to potential categories we never explored, and basically presents us with astronomical sources we never considered. And if confirmed, the superkilonova model proves an entirely new stellar evolutionary pathway that seems to form really bizarre and really tiny neutron stars. And so hopefully, if such an event happens again, researchers will get to observe it with telescopes like the James Webb, because here, by observing infrared light, it might become possible to confirm the composition of the explosion and specifically discover certain elements mixed inside the supernova ejecta. And so by knowing the composition of the ejecta, it may become possible to confirm certain observations. Right now, we unfortunately only have color.
Hello wonderful person, this is Anton, and today we're going to be discussing the discovery, a very recent discovery, of an extremely interesting pulsar. Very likely the youngest pulsar ever found, but also the most powerful pulsar visible from millions and millions of light years away from us. Although in this case we're not really talking about the pulsar itself, not about the neutron star, we're talking about the unusual phenomenon that surrounds the pulsar that you can kind of see right here, known as the pulsar wind. The phenomenon that ends up producing extremely powerful radio waves and a lot of other emissions that are visible from very far away distances. With the most iconic one being this one right here, from our own galaxy, the Milky Way. This is the Crab pulsar. And I actually wanted to start here before I explain to you what the scientists recently discovered. Because Crab pulsar by itself is one of the most mysterious, yet one of the most fascinating objects in the entire galaxy. With the pulsar itself being so tiny that it's actually invisible, but being so powerful that it actually ends up producing these very beautiful waves you see, creating a kind of a standing shock wave known as the wind termination shock. Here's what it sort of looks like accelerated and from a slightly different angle. And so in this case, when the wind coming from the center of the pulsar decelerates to subrelativistic speeds, it ends up releasing tremendous amounts of radio energy that technically is visible from super far away distances. And today we usually refer to these objects as pulsar wind nebula, sometimes also known as the Plerion, a Greek word meaning fool. In essence, it's a type of a nebula occasionally found inside the shell of a supernova remnant that also hosts a neutron star right in the middle. With all of this being powered by the central pulsar and its extremely fast rotation. And usually these are found in optical light, they're also found in sub-millimeter and infrared light, but they also release a lot of radio waves as well. Sometimes they produce higher frequencies such as gamma rays. But they also evolve really quickly and they do change within just a few years. But what's interesting about the Crab pulsar right here is that we know that it existed for at least 1,000 years, or just a little bit less than that. As a matter of fact, back in the days, the scientists figured out when this happened. They were actually able to connect this to ancient observations and ancient entries from China from the year 1054. When the Chinese astronomers reported the so-called visitor star. And today it's believed that it might have resembled something like this. It was probably super bright and extremely hard to miss. As a matter of fact, it was reported by a lot of different Asian astronomers, and even today is still visible if you have a smaller telescope and a dark enough environment to observe all of this. But what's really strange about the supernova is that it was never reported in the West. None of the Western records seem to show it. And at least one study that you can find in the description below explores the idea behind this and potentially finds one mentioning of the star after all. And in short, the study explains all of this pretty well. Early Christian scholars very likely did not want to raise attention to something that's changing in the night skies, because it would basically violate some of the things they believed in. And it would also create a lot of problems for the early church and the early Christianity. And so nobody in the West dared to write about it or to express it in any way. But the scientists behind the study discovered that there were certain coins that were minted during the reign of the Constantine IX in the Byzantine Empire that seemed to contain an unusual star, potentially representing this particular supernova. And was actually only the coins minted between 1054 and 1055. A lot of other coins did not have this star. There were actually two stars in this particular coin, one being Venus and the other very likely being the supernova. And interestingly, the size of the star does differ between 36 different coins that were examined, with the explanation being that the supernova dimmed with time, which changed the appearance of the star on these coins. With the study going into a lot of detail explaining why they believe so, and why they believe that this is indeed the representation of the supernova that happened in 1054, that we now know formed the Crab Nebula. The nebula that even after 1,000 years still produces a lot of radiation and is still actively used for a lot of different Pulsar or pulsar wind studies. But generally it's believed that it's really just after the supernova that this particular nebula is usually the strongest. And so as the pulsar wind ages, the supernova remnant dissipates and eventually can even disappear. But over time it can also transform into something a little bit different, sometimes referred to as the bull shock nebula, surrounding various millisecond or slowly rotating pulsars. The bull shock nebula generally produce very different features and are also not as easily visible from faraway distances. But in these objects, pretty much everything happens because of the rotation of the pulsar and because it tends to accelerate things so much in the center. And all of this is very likely due to very powerful magnetic fields that tend to accelerate various plasma particles to relativistic speeds, speeds close to the speed of light. And so in some sense, these very powerful pulsars act like very powerful magnets, so kind of like magnetars. Although the actual features on the inside and exactly how all of this evolves is still poorly understood. And very recently the scientists that were actually studying all of these objects by using the survey known as VLAS have discovered one of the youngest such stars inside one of the brightest and the most powerful pulsar wind nebula ever seen. The pulsar wind nebula is so powerful that it seems to be visible from roughly around 395 million light years away from planet Earth. And up until the year 2000, this particular survey did not actually show anything coming from this region. The scientists believe it's because the supernova has just occurred, with the star basically reaching its limit and exploding, expanding all of the material away from it. But the neutron star itself, along with a lot of the materials surrounding the neutron star, was still behind a relatively dense shell of debris that was expanding from the supernova explosion. In other words, following the explosion, we still were in a stage where a lot of this was still invisible. But starting in 2018 up until now, new images revealed some kind of a very powerful object that was clearly visible and very bright in the radio frequency of 1.5 GHz. And because this is approximately 20 years apart, the scientists believe that this pulsar could be as young as 14 years old, making this the youngest pulsar, the youngest neutron star, and also very likely the youngest pulsar wind nebula we've ever discovered. And it's very likely a pulsar wind nebula because the neutron star or a pulsar by itself should not really be that bright from 390 million light years away from us. It does require a different mechanism such as the nebula around it in order to create so much luminosity that it's visible from many different places in the universe. Here's by the way where all of this is located. It's a dwarf galaxy briefly known as SDSS J113706, and it's a dwarf galaxy known for a lot of star formation, which means that there are probably a lot of supernova and a lot of neutron stars and black holes being formed pretty regularly, pretty much every single year. And because this neutron star very likely possesses very powerful magnetosphere, overall it seems to appear about 10,000 times more energetic than the Crab Nebula, or 10,000 times brighter than what we have right here in the Milky Way. Which brings up an interesting question. Was the Crab Nebula as powerful when it was just created around 1,000 years ago? And if not, why not? Was it because the neutron star in the middle was different in some way or another? For example, maybe what was produced in this case was not just a neutron star, but an actual magnetar, the most powerful magnet in the universe. Which also means that maybe this is how we could one day answer the question of mysterious fast radio bursts. But that's another question we're going to be answering in some of the future videos. And if this is a magnetar, why was it produced in this case, but not in 1054 inside the Crab Nebula? Or maybe this was a magnetar in the beginning, but then it transformed over time, losing all of its magnetic energy and eventually becoming the pulsar that it is today. So in that sense, we don't actually have a direct answer just yet. But if the scientists start detecting unusual fast radio bursts or some other radio emissions coming from this new neutron star as well, it might actually help us answer so many different mysteries all at once. Mostly because, well, officially this is now the youngest neutron star in existence, and definitely one of the most powerful and one of the most intriguing neutron stars surrounded by a pulsar wind nebula that we've ever been able to find anywhere in the universe. And so investigating this more, or looking for more emissions coming from here, could be the next important step in trying to understand what happens during these extremely powerful supernova that end up producing these very powerful nebula.
Some of the most bizarre and some of the most beautiful formations in the entire galaxy are usually formed by pulsars. For example, the iconic Pulsar nebula formed by the Crab Pulsar, or the super strange Hand of God, that's also the result of a Pulsar nebula forming a really bizarre structure. And that's on top of so many other mysteries around pulsars that we're still trying to understand and still trying to explore. For example, the discovery of these super strange radio lines all over the Milky Way galaxy, thousands of which have been discovered all over the place, has now also been linked to various pulsars, as we'll discuss in some of the videos in the description. And the discovery of several strange structures, resembling bullets moving through some kind of a nebula, also seem to be the result of fast-moving pulsars, which seem to have acquired their velocity as a result of an ancient, powerful supernova. This is the famous cosmic cannonball. And even more recently, NASA identified this really strange structure, now referred to as the cosmic guitar, mostly because of a very strange shape resembling a guitar, which seems to be once again formed by a fast-moving pulsar escaping some kind of an ancient region, where once again it was probably formed by some kind of a supernova. This is one of the more recent discoveries coming out of NASA's Chandra Space Telescope. Not to mention that the first exoplanets ever discovered were also found around a pulsar as well. This is the famous PSR B1257 system. And so with so many strange, bizarre, and somewhat difficult to explain discoveries, pulsars have always been some of the most mysterious objects in cosmology, and researchers are always eager to learn so much more about them, just because they seem to form so much weird stuff. And well, in this video, we're going to discuss one of the recent discoveries that possibly solves at least one mystery, but in the process discovers something else about pulsars that is kind of surprising and even shocking. They might have mountains. And mountains that seem to be made out of something super strange. And so let's talk about this in a bit more detail, but first let's start with the slightly different study in regards to the famous Crab Pulsar I showed you previously. One of the most studied objects in the night skies, and the object that was created in 1054 AD by a massive supernova 6200 light-years away from planet Earth. And well, because this is a pulsar, naturally it has to pulsate. And here it seems to do so 30 times per second. Here's a slow motion video of this, taken by the researchers from the Cambridge University. But turns out that this pulsar also produces some other bizarre patterns that up until recently were kind of difficult to explain. And specifically, it seems to produce these zebra-like patterns that only recently have finally been explained in a study in the description. Turns out that this is a diffraction pattern, or basically a type of an interference, caused by different levels of plasma around the pulsar's magnetosphere. In other words, by seeing this pattern, it now becomes possible to kind of scan the environment around the pulsar, which in theory should help us produce some kind of a three-dimensional image of this, once someone figures out how to use this. And so in other words, by using these very precise signals, and by seeing deviations inside the signals, it starts to become possible to figure out what happens around the pulsar, allowing us to directly map this object by seeing how these signals differ every single time. And it's really always been these signals that taught us the most about pulsars. Mostly because here, even minute deviations usually tell us that something is going on or something is very different. And while in the last few years, because of the advances in radio telescopes, researchers started to discover this somewhat bizarre mystery. Some of the pulsars were pulsating way too slow. As in, they should not even be pulsing at all, yet they were. And that's because based on modern theories, the only reason neutron stars even pulsate is because they're spinning so fast. In other words, the pulsar's energy comes from its spinning motion, and these radio emissions are only produced because the pulsar is spinning fast enough. And based on the modern calculations, it's actually believed that the pulsar has to spin at least once every 10 seconds to produce these radio pulsations. So basically, if a pulsar starts spinning too slow, more than once per 10 seconds, it reaches what's known as the pulsar death line. Technically, this is when the radio emissions stop, and the pulsar just becomes a regular neutron star, which is what scientists believe happens to pretty much most pulsars with time. Eventually, they lose their rotation speed, and eventually they become quiet. And that actually makes sense, because if this didn't happen, we would be seeing millions if not billions of pulsars all over the place. Because based on the age of the Milky Way galaxy, and based on the amount of certain types of supernova, we do expect at least 1 billion neutron stars in the entire galaxy. But we've only discovered just over 3,000 pulsars in the Milky Way, suggesting that they do eventually stop pulsating and become quiet. Here's roughly what the modern map of these pulsars looks like if you were to look at the entire Milky Way. But as I mentioned, for some reason, in the last few years, researchers also discovered a few pulsars that were just spinning way too slow. For example, one of the pulsars, approximately 2600 light years away from us, seems to only emit radio pulses once every 18 minutes. This is now referred to as a long period transient. And quite a few of them have been discovered in the last few years, with periods ranging from minutes to hours. And though some of these objects have been explained as potentially being white dwarfs and not neutron stars, in many cases they're just way too powerful to be anything but a neutron star. And so because a handful of these objects have not been discovered, researchers have been trying to figure out how this is possible, what's actually going on, but more importantly figure out what mechanism is responsible for producing these radio waves. Because here this goes beyond explanations involving pulsars, and the rotational energy is just not enough to produce these signals. And here we have at least a couple of new studies that possibly present us with certain explanations. And so in this first study, we have a detection of a pulsar with a 41-second period that bridges the gap between classical pulsars and these long period transients. And so because of this intriguing object, researchers started to look for more and did actually discover quite a few of them, suggesting that there seem to be quite a few of these objects that are difficult to explain using classical explanations, but also seem to represent this bizarre missing link connecting various pulsating objects. And it was really this recent study that you can find in the description that potentially provides us with maybe one explanation that kind of makes sense. Based on two more examples of these slow-moving pulsars, researchers realized that it's possible for these neutron stars to produce these signals if they're not perfectly spherical. Or to be more exact, if they contain deformations on the surface, deformations resembling super tiny mountains. And because neutron stars are generally only about 10 to 12 kilometers across, here when we say mountains, we're talking about objects that are only 1 centimeter in height, or basically just a fraction of an inch. And so here these super tiny mountains would technically be enough to produce these really bizarre signals. And that's because on a typical neutron star, the gravity is at least 100 billion times stronger than planet Earth. And because of this, even a tiny feature, millimeters or centimeters in size, is going to produce dramatic effects. And so in this recent study, researchers from the Peking University developed a computer model in order to find out how these mountains might affect electric fields around various pulsars. And turns out that by having these tiny mountains, it would start affecting the path of positrons and photons, with mountains that have steep slopes dramatically amplifying local electric fields, allowing these neutron stars to once again become pulsars, because suddenly these particles would be accelerated to tremendous speeds. And so because of this particle acceleration, various electrons and positrons start to create radio waves resembling pulsating waves once again. And so these very unusual deformations on the surface, in theory, can concentrate the electric field so much that it can produce a powerful beam on any neutron star. And so even neutron stars that rotate really slowly will suddenly reach the energy threshold to trigger radio emissions once again. And if this idea is correct, it can provide certain clues about what's happening on the surface of these bizarre objects, specifically what they're made out of. Because in order for these mountains to survive and not to become completely flattened, they have to be made out of something incredibly strong. And that's because ridiculously powerful particles that crash into the neutron star all the time will eventually erode any matter present on the surface, making it super smooth. Unless this is made out of something really strange. For example, the Strangest matter, an exotic form of matter that's bound together by strong force and is extremely difficult to destroy by any interaction. And that's because most particles are usually connected through electromagnetic forces, and so your typical matter and your typical molecules, which usually rely on electromagnetic forces to stay together, would not produce enough energy to destroy these Strangest particles. And here Strangest is kind of similar to a nucleon. Nucleon is what's inside of us, and that's usually made out of protons and neutrons. But a Strangest would be a combination of strange quarks and up and down quarks. You can read a little bit more about this and some of the propositions about this in the study on the Strangest matter or the Strangest stars. Both studies are in the description below and basically discuss how this unusual matter might explain quite a lot of things we see about neutron stars, proposing the Strangest stars and even hybrid stars as a new type of an object. And so the idea here is kind of similar. Maybe by having these Strangest particles that are strong enough to survive pretty much anything, they might start forming various mountains on neutron stars, which then produce the radio signals we seem to observe. And if the researchers behind the study are correct, it can also explain a lot of other stuff we've been observing. For example, neutron star glitches. When various neutron stars suddenly change their spinning speed, it might actually be connected to either formation or destruction of various mountains on the surface, or possibly formation of Strangest matter from some of the regular matter on the surface. Likewise, this might also help us explain a lot of other mysteries, including fast radio bursts, which usually also come from neutron stars. And so in terms of theoretical propositions, this one is kind of exciting. But in order to prove this and in order to confirm if this is real or not, we definitely need more observations, more analysis, and a lot more detections of these bizarre stars by various powerful radio telescopes. Hello wonderful person, this is Anton, and today we're going to discuss some of the recent discoveries and some of the new mysteries in regards to the already mysterious objects known as Magnetars. The objects representing some of the most exotic matter in the entire universe, and the objects whose properties are so extreme that they are basically impossible to imagine using any earthly comparisons. And specifically, we're going to be discussing the object discovered right here in the Milky Way galaxy, whose origin is currently unknown, but whose discovery might provide an explanation for the other mystery of cosmology referred to as FRBs, fast radio bursts. And so let's discuss this in more detail, but first, what exactly is a magnetar if you've never heard of this before? And well, it's actually really hard to imagine. But basically, it's a collection of some of the most extreme matter in the universe condensed into such a small volume that if it was actually even smaller, it would turn into a black hole. And though it is kind of similar to a neutron star, they also seem to possess many properties that neutron stars do not have. For example, out of approximately 3,000 known neutron stars, many of which have been observed as radio pulsars, or basically they create these radio emissions visible from planet Earth, only 30 so far have been identified as magnetars, that though also sometimes emit radio emissions, seem to produce emissions in a lot of other frequencies, including X-rays and gamma rays. And even though a typical neutron star is already quite magnetic, with a typical pulsar potentially being at least 1 trillion times stronger in terms of magnetism compared to planet Earth, a typical magnetar is at least 1,000 times stronger still, making these literally the most powerful magnets in the entire universe. One scary comparison I've heard before is that if you were to somehow find yourself approximately 1,000 kilometers away from a typical magnetar, you would literally die instantly, because the strength of the magnetic field here would cause every single atom inside one's body to completely fall apart. But because only 30 such objects have been officially confirmed, there is still a lot of mystery about them, and especially about their origins. Even though it's assumed that they're created through supernova, this has never been confirmed, and the actual mechanism of their formation is still not clear. As a matter of fact, in one of the recent studies in the description, we've discussed a potential formation that's not a supernova, that basically involves different types of star collisions, but even that is still uncertain. But in the last decade or so, many different unusual exotic emissions from across the universe, including the mysterious fast radio bursts and various types of gamma ray bursts, have basically been explained as magnetars potentially doing something unusual we've never seen before and possibly experiencing some kind of an exotic event, because a lot of these emissions otherwise make no sense and there is really no way to explain them unless we use magnetars. And one such bizarre detection happened not so long ago in 2024. Here there was a really strange, ultra-bright explosion. This was coming from a famous galaxy known as M82, also referred to as the Cigar Galaxy. And so at a distance of 12 million light-years, this was a very unusual and very unexpected detection. And it was basically a blast of super high energy that lasted a fraction of a second, but was extremely violent and extremely powerful. Here the amount of energy was equivalent to a relatively small supernova. But there was no actual supernova, and at first it was not clear what's really happening. And though here the event resembled a typical gamma ray burst, it was a little bit different. And eventually all of this was traced back to a magnetar, and actually the first ever confirmed extragalactic magnetar located outside of the Milky Way. And so this very strange ultra-bright explosion turned out to be the result of a very strange starquake, which seems to happen when the magnetar's super powerful magnetic field changes the star spin just a little bit, dramatically disrupting its outer layers, which then resulted in this powerful explosion or this giant flare that released a lot of gamma rays in less than 1 second. And to date this is the third such event discovered, with the other one being in the Milky Way and the third one being in the Large Magellanic Cloud. So basically after 50 years of observations, it's now been officially confirmed that a lot of these starquakes on magnetars can result in some ridiculous emissions resembling gamma ray bursts and potentially a lot of other explosions, including fast radio bursts. And they've actually been connected to many other anomalies in regards to various emissions, including what's known as AXP, also known as anomalous X-ray pulsars, which are basically pulsars that seem to emit X-ray radiation and tremendous emissions of X-rays that at first made no sense. Only a few have been discovered so far, but once again magnetars seem to be the best explanation. And so in essence we have many different powerful emissions in many different wavelengths, with really only one culprit behind all of them. They all seem to be the result of various activities inside magnetars. But here's the thing, as I mentioned in the beginning, we actually still have absolutely no idea what magnetars are, or specifically how they form. With the recent study that we're going to be discussing now, essentially confirming that it possibly is not the result of a supernova. In other words, unlike other neutron stars, there's a very high chance that magnetars seem to form in other ways, or at least some magnetars do not form from supernova. And here the story starts with a magnetar discovered a few years back, originally seen by the Swift Observatory. This was actually found back in 2008, and this is the original image. Here this was first detected as a soft gamma ray repeater, or essentially a kind of a gamma ray pulsar. It was detected because of these very intense flashes of gamma rays coming from the outskirts of the Milky Way galaxy, and eventually was confirmed to be one of these 30 magnetars known to us, now referred to by this name. And while approximately a decade ago, researchers also discovered a supernova remnant not so far from this object, which several studies linked to this magnetar, suggesting that this is maybe how it was created. At first all of this kind of made sense, but this was of course based on slightly older assumptions that supernova and magnetars have to be connected. As a matter of fact, one of the older assumptions was that magnetars are just basically extremely young neutron stars, possibly the result of extremely recent supernova that happened in the last few thousands of years. With the other assumption being that as magnetars get older, they essentially stop being so magnetized and potentially become either pulsars or just typical quiet neutron stars. But these assumptions were not based on evidence, and the evidence from this magnetar seems to point at something entirely different. And so in this recent study, the team you see right here revisited this magnetar once again, specifically focusing on its motion across the night skies by using the observations from the Hubble Space Telescope. Now, because this magnetar was essentially kind of in the middle of nowhere, but somewhat close to the supernova remnant, it was initially assumed to be coming from inside. But after 12 years of observations using Hubble and by tracking the motion across the night skies, the magnetar's position and its trajectory seem to actually be very different, as in its apparent motion was not coming from the supernova remnant, and the magnetar was not associated with any remnant anywhere. And when the scientists tried to trace back the motion several thousand years, they basically found nothing in the pathway, or really anything that could explain the existence of this magnetar. And that created a bit of a mystery, but also a potential solution. First of all, this implied that this magnetar either has to be really old, much older than 20,000 years old, and coming from somewhere entirely different, which already contradicted some of the previous ideas about magnetars. Or maybe this magnetar was produced by some kind of a very low energy supernova that left almost nothing behind it, which basically kind of also didn't make sense because we should see something. Or, more likely, here the magnetar formed through a very different process that has been previously explored in other studies, and basically involves a merger or a white dwarf turning into a neutron star through a process of accretion, which currently is the best possible explanation and actually provides an explanation for many different mysteries across the universe. And this is based on two formation theories that have been proposed a few years back, but the evidence for which did not exist until now. For example, it is possible for a magnetar to form if two much smaller neutron stars collide and do not result in an explosion known as kilonova. By itself, this would be a very rare event, but it is possible. However, a much more likely situation here is something we've actually seen many times. This could be a result of the accretion process around a really massive white dwarf. And these types of systems do exist in many locations in the Milky Way galaxy. Basically, here we have a white dwarf consuming a lot of mass from its partner, and usually resulting in some kind of a nova once in a while. But in a situation where it basically reaches a critical mass, these white dwarfs are expected to explode, but not always. Sometimes they can also collapse, and if they do collapse, they should produce a neutron star as well. But several models examining this resulted in the production of an extremely magnetized neutron star, which would resemble a magnetar in every single way. And so the best explanation for the existence of this magnetar is what's known as accretion-induced collapse. If this proposition is correct, there actually should be still presence of some kind of a companion nearby, and signs of this should be visible in some of the future observations. But most importantly, if this is actually confirmed, this would serve as a very important step in explaining so many mysteries coming from different regions in the universe, specifically things like fast radio bursts and different types of gamma ray bursts that occasionally came from regions where they should not exist. Not so long ago, we've discussed some of the more mysterious FRBs that seem to have come from locations where there are basically no stars, or at least no visible stars. But white dwarfs with partners can technically exist there, and in theory should be able to produce a magnetar that could then once again result in a very powerful explosion like the one seen from the M82 galaxy. Basically the result of some kind of a starquake on the surface. And so when it comes to astronomy, and when it comes to mysteries of different signals, right now this is a super exciting discovery that provides a very important piece of evidence. Since we found one of these objects right here in the Milky Way galaxy, chances are they do exist everywhere, and chances are a lot of powerful emissions and powerful explosions such as gamma ray bursts, superluminous supernova, and fast radio bursts all come from very similar magnetars in the middle of nowhere. And because this object is approximately 15,000 light-years away from us, it now allows us to study them in more detail and possibly resolve so many mysteries in astronomy all at once. Unless, of course, someone does discover some kind of a supernova remnant where this object potentially came from, which would unfortunately invalidate this hypothesis.
Hello InfoPerson, this is Anton, and it's time to have our update in regards to FRBs, or mysterious fast radio bursts. These still unexplained mysterious radio signals coming from pretty much everywhere, that though only discovered in 2007, have now been found in much higher numbers, just because we finally know what to look for. And these signals are exactly what they sound like. They're extremely energetic flashes of radio waves that seem to only last for a millisecond or two, and in some cases even shorter. But in that tiny fraction of a second, a typical FRB can produce more energy than the entire sun emits in 1 year. But in some of the recent studies, as we're going to be discussing today, researchers found something that was even more powerful and something that was even more extreme, which is what we're going to be focusing on today, discussing some of the more bizarre discoveries in mid to late 2025 and talking about some new record holders. And that's because in the last few months, driven by powerful new telescopes, we essentially entered a new era of fast radio burst science. And even though for many years these were just signals coming from somewhere, but scientists were not entirely certain from where,
Based on some of the new studies and new observations, at least some of these FRBs have now been pinpointed to exact galaxies and even parts of galaxies where they seem to have come from, essentially hinting on what possibly produced them and how most of them seem to be created. And so let's talk about some of these studies that, as always, you can find in the description. But in this case, let's actually start with something more practical, or I guess why FRBs even matter today and how they're helping astronomers from other disciplines. And that's because these millisecond pulsations can also be used for additional studies, especially when it comes to mapping things. Because of their very specific emissions, and because there are so many of them coming from so many different places, it actually becomes possible to use them to map the invisible parts of cosmos and to see certain structures that would be otherwise invisible. And for many decades, this was a bit of a problem because some stuff, especially some of the more diffuse gas, is almost impossible to see. As a matter of fact, when comparing theoretical predictions about the mass of the universe and comparing this to the actual observations, for many decades there was actually something missing. And not just dark matter, actual matter was missing too. For many years this was referred to as the missing baryon problem. Or just to rephrase this, even though we see a lot of gas and a lot of dust and a lot of galaxies and stars around us, technically there should actually be at least twice as much. And so half of the mass was missing and nobody knew where it was. And that's of course on top of the other missing stuff like dark matter. But turns out that over the years, there was a way for us to find this mass and to see it directly. So it wasn't really missing, it was just very difficult to see. And mostly because it was very spread out and located between galaxies. And some of the first hints we've actually discussed in some of the previous videos in the description revealed that it was, as I assumed before, hiding between galaxies. And that's where FRBs come in and help us confirm this once again. Because here they act like cosmic flashlights. As the radio signal travels across billions of light years of space, and as it passes through certain parts of gas, this will usually change certain wavelengths to stretch and to disperse just a little bit. And so here, by precisely measuring how much the light slows down and how much it changes over time, it then becomes possible to estimate the amount of gas it passed through. And so in this recent study, Liam Connor and the team you see here used 69 localized FRBs to confirm that there was a lot of matter they passed through and a matter that was otherwise invisible. Essentially confirming that as those FRBs traveled toward us, they passed through huge amounts of dust, and confirming that 76% of the universe's normal matter or baryonic matter seems to be floating in the intergalactic medium and is outside of galaxies, not inside of them. With this discovery officially once again confirming that the missing matter is between galaxies, as it was always assumed. And that was a really important confirmation for cosmology, and really only possible because of these observations of FRBs and what we've learned about them in the last few years. But, as I mentioned, we also have some really extreme FRBs detected in the last few months, and some of them are creating new mysteries. Because in the last year alone, astronomers broke records in both distance, proximity, and even brightness when it comes to these bizarre radio signals. And here I guess let's start with the most distant FRB detected ever, reported in this study by Manisha Caleb and this whole team here. This is the FRB known as 2024-0304b, and looks like it came from somewhere right here. This is when the universe was only about 3 billion years old, during the time known as the cosmic noon, and also during the time when the star formation most likely peaked, with most galaxies generating most amount of stars. And here the distance is nearly 18 billion light years away from us, making this quite a significant discovery. Mostly because it essentially doubles the previous record, and also suggests that FRBs existed back then as well. And naturally, because it traveled through so much space, by studying the signals in more detail, it will probably become possible to determine what it also passed through. So what kind of gas, how much gas, and so on. But here, additionally, by using the James Webb Space Telescope, researchers also analyzed the host galaxy, discovering that it seems to be very low in mass, seems to be relatively young, but is also forming stars very rapidly, with this environment strongly supporting the leading theory for the formation of FRBs, basically Magnetars. we do expect these types of galaxies to contain a lot of magnetars, and so at least some of them could potentially produce FRBs. And if you'd like to learn more about why we think it's magnetars, check out one of the previous videos in the description, and in this case it was a discovery of an FRB coming from our own galaxy where we know there is a magnetar as well. And so this was definitely quite an intriguing discovery, at least in terms of distances. But then, around the same time, there was actually surprisingly another record holder from a completely different galaxy and, of course, different period of time. In March of 2025, the Canadian experiment known as CHIME detected a burst so powerful that researchers decided to give it a kind of a playful nickname, referring to this as an RB float, short for Radio Brightest Flash of All Time. And you can learn more about this in this study that involved quite a lot of different sciences. And so here, FRB 2025-0316A was so bright that at first researchers thought this was just radio interference from maybe some kind of an airplane or cell phone nearby. So basically this is how powerful it seemed to be. But eventually it was determined to be real, it was confirmed to be definitely an FRB, and was even traced back to the galaxy known as NGC 4141, 130 million light years away from us. It's the galaxy that hasn't been studied a lot, but it kind of looks like this. And so here, by using new techniques, and specifically by using a synchronized network of telescopes across North America, the team was able to achieve unprecedented level of precision, pinpointing the entire source to the region of about 40 light years. And given the distance here, this accuracy is absolutely ridiculous. Here it's basically like observing a tiny coin at a distance of 1,000 kilometers. But crucially, unlike some other FRBs, this one was non-repeating. And that's extremely interesting because trying to pinpoint a location for a non-repeating FRB is usually super difficult, mostly because by definition, they only happen once and only last for a fraction of a second. And here the location seems to suggest it came from the spiral arms, but surprisingly not in the nearest star-forming region, suggesting that maybe either this was not from a magnetar, maybe from a different source, or that the magnetar was kicked out, possibly because of the interaction with other stars, or possibly because of supernova. And that's something that's not impossible and has been observed before. Although I guess let's also briefly discuss why scientists think that this is a magnetar, and why right now this is the best explanation we have. And technically this is not just theoretical anymore, because we do seem to have actual evidence based on some of the bursts observed. And specifically at least one of the bursts, located 200 million light years away from us, was studied something known as scintillation, or basically how much the light is sparkling as it moves away from the source toward us. You can actually think of it as twinkling of a star, but in this case in radio waves. And this is something we discussed in one of the previous videos, but in essence, based on scintillation or the degree of twinkling, the size of the object in this case was constrained to be at most 10,000 kilometers. So it had to be a really small object, but with a lot of power and able to emit a lot of energy all at once. And at this particular size, well, technically it could be something like a white dwarf, but it just would not have enough energy, so it's most likely a neutron star. But because these emissions also signify very high magnetic fields, here the explanation is that these FRBs seem to emerge from neutron stars' magnetosphere, very likely because of some kind of powerful events happening on the surface of the magnetar. Now exactly what happens is still uncertain, but quite a lot of propositions have been suggested, including maybe collisions with objects such as tiny asteroids and tiny planets. And some of these very similar conclusions have also been reached last year when researchers from Australia using the Australian radio telescopes, such as for example the Murchison Wide Field Array, discovered the presence of a lot of polarization, and actually quite diverse polarization, that must have come from very, very powerful magnetic fields that we believe can only exist around magnetars and nothing else really. And so here many details confirm that the energy coming from these objects seems to originate from extreme magnetic fields close to very compact objects less than 10,000 kilometers in size. So basically a definition for a magnetar. And that's something that's been confirmed in many studies and seems to be the best explanation we have as of 2025. And then last but not least, we also have this bizarre discovery of a hyperactive FRB, or basically a repeating fast radio burst that in this case is just a little bit overactive. This is referred to as FRB 2024-0619D, and it was originally discovered by the South African Meerkat. And here the first three bursts were detected within just the first 2 minutes. But the emissions and the signals kept repeating once again, and within just the first week, scientists discovered nearly 250. This is basically the most signals detected from a single source in such a short time, although obviously all of the signals were just a little bit different. But here the origin and the explanation is still not clear. Technically this is very similar to other FRBs, but because currently there is no optical counterpart, or basically nothing else is visible in any other frequencies except for radio light, right now we don't really know what's happening and why this object is so active. We just know that it seems to have a lot of repetition, and repetition that seems to be clustered in time. Or basically these signals seem to happen in chunks, sometimes even entering something scientists refer to as a burst storm. And this is when the source suddenly switches from being inactive or quiet to suddenly becoming hyperactive. And so here in June of 2024, it was able to produce 250 bursts, but that was just after 4 hours of observations. It's quite likely there were way more that were just missed. But once again, because a lot of this was highly polarized and coming from a very small source, right now powerful magnetospheres and very likely Magnetar magnetospheres seem to point at the best explanation. So for example, maybe there was just something orbiting around this Magnetar, or something that's slowly falling into it, dropping one piece at a time, such as for example some kind of a planet that's falling apart and is slowly being absorbed by the Magnetar, or maybe this is something in regards to its environment and where it's currently located, with these emissions being the result of some kind of a high-density cloud that the star is flying through. So I guess in short, at the moment, the signal itself is very mysterious. But that's why I loved making these videos about FRBs, because pretty much every year, and now every few months, we seem to find new mysteries and new record holders, with some of these objects still not really making a lot of sense. And though as I mentioned, the best explanation is still a Magnetar, in reality, we don't really know what's happening, and even the Magnetar model cannot explain everything we're observing. Hello wonderful person, this is Anton, and today we're going to discuss a somewhat intriguing study that claims to have discovered evidence for a very bizarre type of a star, literally known as the strange star. And it's actually called that because of its properties and because what it's made out of, specifically strange quarks. And because in this case this is based on some of the more recent observations, and observations from a very peculiar explosion, surprisingly right now this is actually one of the best explanations. And so let's discuss this new discovery in more detail, but I guess let's start with the explosion itself first, and why it was kind of strange. And well, technically here there's not much to see, mostly because this was a gamma ray burst. And in this case a gamma ray burst that very likely happened billions of light years away from us, but was detected on May 29th, 2024. And just like with many other gamma ray bursts, this was almost right away picked up by a lot of different facilities. As a matter of fact, you can find the list of all of the reports about this event in one of the links in the description. There were 35 separate observations from different facilities and using different wavelengths, which actually highlights that we've technically entered the golden era for various detections in astronomy, and specifically detections of gamma ray bursts. But when it comes to the origin of these events, there are still some unanswered questions, and specifically questions in regards to their origins, because a lot of gamma ray bursts produce different observations. Some of them can be very short, some of them last much longer, and some of them produce different wavelengths. And so today scientists believe that there might be at least 4 separate sources. The first obvious one is a massive supernova, or specifically a star collapse, that produces 2 very powerful jets. Or maybe this is some kind of a very powerful black hole, specifically a hyper-accreting black hole, that's spinning very rapidly and produces powerful jets as a result. Or this is a collision of 2 neutron stars, which has been previously detected and confirmed to cause short gamma ray bursts. Or lastly, this could also be the result of some kind of a magnetized neutron star, or a millisecond magnetar, that seems to undergo some kind of a major change. And so depending on the source, gamma ray bursts might appear a little bit different. And well, the thing is, this recent gamma ray burst was actually kind of bizarre. And here it was bizarre because it seemed to produce several separate emissions. And specifically, it seems to have produced 2 separate episodes, with approximately 400 seconds of quiet time between them, as if there were actually 2 explosions. This was observed by different telescopes and confirmed by different studies. And so this bizarre event with 400 seconds of quiet time doesn't actually make a lot of sense, at least using previous explanations involving black holes, colliding neutron stars, magnetars, or supernova. Here's actually one of these previous observations that even shows us potentially another event that happened approximately 100 seconds after the first explosion. And so in this recent study, Xiao Tian and his team proposed a really intriguing explanation that kind of matches all of the observations. What if this was actually a formation of a very bizarre object we usually call a strange star? A theoretical concept in physics where basically as stars get more and more density, at some point even neutron stars start to change into something else, changing all of their neutrons into quarks. And following this, if there's even more density, transform into different types of quarks. Okay, it might sound complicated, but basically here's what scientists think might happen as matter becomes denser and denser and as it reaches its limits before it turns into a black hole. We know that following certain types of supernova, the remnant becomes a neutron star, or basically a star where all of the protons and electrons combine, leaving behind nothing but neutrons. But previous studies have also proposed that inside these neutron stars, especially at very large depths, even these neutrons, because of the pressure, will start transforming into something else. They'll actually start losing their confinement and will suddenly create a notion of quarks. So essentially those elementary particles everything is made out of. Here we're mostly going to have up and down quarks, but potentially some other types, because quarks tend to change into one another. But as the star becomes more and more dense, eventually most of the neutrons potentially convert into quarks, creating a hypothetical quark star. A star that might have some neutrons as the crust on top, but the insides are all quarks. In terms of mass it's going to be the same, but in terms of size it's going to be a little bit smaller. But this is not the end of the story, because as you condense quarks more and more, they'll actually transform into something else in order to achieve stability. And so at super high densities, all of the quarks start to change into strange quarks. In physics, this process is known as deconfinement, and it's essentially a kind of a dissolution of subatomic particles that first makes quarks free particles, but eventually forces some of these quarks to combine into strange quarks, forming more and more of this strange matter. And the more density the star has, the more strange matter is going to have. Once again, just to clarify, this is only called strange matter because of the name of the quark, not because it's unusual or because it's weird. And it turns out that this particular matter is extremely stable. So stable, as a matter of fact, that once something becomes that, it's unlikely to change into something else unless there is some kind of a black hole nearby. And though it's possible for this strange matter to collapse further, forming a black hole, in theory these stars can exist for a very long time without changing anything. But all of this was basically just theory. Up until recently there were no confirmations or really anything to actually suggest these stars exist. But once in a while we discover something here and there that seems to match predictions about these strange stars. For example, a couple years back, scientists discovered this bizarre compact object, with the name you see right here, that surprisingly resembled what we thought a strange star might look like. Mostly because this seemed to be some kind of a neutron star, but it was just extremely low in mass. It was about 77% of the solar mass, but extremely tiny in size and producing huge amounts of energy, while also being surrounded by a supernova remnant. And even today there is still no better explanation for what exactly this is, but for all we know, this is maybe one such star right here in the Milky Way galaxy. But this new observation is unique for a different reason, because here we might have finally seen how these unusual objects are created, assuming of course scientists behind this paper are correct. And right now their explanation is technically the best. Because in this case, once again, it's difficult to explain why this explosion contained at least 2 but possibly 3 separate shocks. These very powerful episodes must have been caused by something absolutely extreme, and so a supernova or even a black hole would not produce this in this way. But here these X-ray emissions definitely confirm at least 3 separate events, powerful events, that happened minutes apart. And so researchers now believe they can explain all of this by combining this with ideas behind strange star formation. And so basically, that first event was the gamma ray burst, and this very likely produced some kind of a neutron star, potentially a magnetar. And intriguingly, following this first emission, there seemed to be some kind of a plateau or some sort of an X-ray afterglow that lasted for just over a minute. And to the researchers behind this paper, it suggests that this could not have been a black hole, and thus very likely involved a neutron star or a magnetar that's about to do something else. And that something else happens right here. This magnetar collapses into a quark star, which results in a second explosion. And then for basically a few more minutes, we see additional afterglow and additional emissions that researchers believe was a stable period, where the quark star mostly contained up and down quarks, but no strange quarks yet. And then finally we have our last transformation, where the quark star turns into the strange star as many up and down quarks transform into strange quarks, and as the quark star goes through a kind of a transition stage. And in this case, the quark star is actually believed to act kind of like a liquid, specifically a very homogeneous liquid, making these quark stars resemble enormous liquid objects. But this liquid stage doesn't last, and the cooling of the quark star starts to transform it into the strange star, with the liquid basically becoming a huge solid, or potentially even a crystal. And researchers here believe that it's this cooling process that we actually observe as the X-ray afterglow, with the final product basically being a strange star in a solid crystal form. Although interestingly, in terms of properties, it's very similar to a magnetar. So the two would be very difficult to tell apart from a distance, with the main difference being the size. It would be just a little bit smaller. So basically, instead of being 14 kilometers, it might be 10. But many papers also suggest that these stars would very likely contain a crust made out of neutrons. And this neutron matter crust, which is also very likely solid, sometimes collapses. And this usually happens when some kind of an accretion happens from the outside, and basically a lot of matter falls onto the surface of these stars. And here, once the collapse happens, this creates a huge cascading effect that affects the entire quark star, releasing a huge amount of magnetic energy, with all of this happening ridiculously fast and very likely producing very powerful radio emissions. And so today this is actually one of the main explanations for what we refer to as fast radio bursts. Hello InfoPerson, this is Anton, and today we're going to be discussing a somewhat bizarre collision, or technically a collision within a collision, that happened billions of light years away from us and resulted in a very powerful explosion. And mostly because extremely recently, NASA actually published this beautiful image showing us where all of this occurred and explaining why this is so bizarre and why this is so unexpected. And here this is a discovery involving a very specific type of a gamma ray burst. These are usually some of the most powerful explosions in the universe. And so here GRB 230906A, officially discovered in 2023, involved a very peculiar explosion that's now helping us solve two separate mysteries in astrophysics. With the first mystery being why sometimes these very powerful flashes seem to have no home or no home galaxy. And the second mystery being why we sometimes find a lot of really complex metals such as gold and platinum in very peculiar locations outside of the main galactic body, which this particular detection seems to explain pretty well. But I guess first let's start with what happened here and what we know so far. And so on September 6, 2023, the Fermi Gamma Ray Space Telescope detected a relatively brief but very intense flash of energy visible in the gamma rays. This was a gamma ray burst that lasted for approximately 0.9 seconds, so basically just under 1 second. And so this was a short duration burst that we normally associate with this. In essence, all of these short duration bursts are believed to be the result of a neutron star collision, a collision between two extremely dense objects. And they almost always produce these ridiculously powerful explosions that actually end up creating some of the most powerful emissions in the universe. But GRBs come in two different types, the long GRBs or the short GRBs. And so the long gamma ray bursts lasting more than 2 seconds seem to be mostly caused by a collapse of very massive stars that eventually form black holes. But it's the short GRBs that are particularly interesting. And that's because they always seem to be the result of a neutron star merger, like the one observed in 2017 that essentially finally solved this mystery. Or basically provided us with enough evidence to confirm that short GRBs seem to be connected to neutron star collisions. And just as a reminder, a neutron star is basically an extremely dense core of an ancient dead star that's usually only a few kilometers across, but contains more mass than the Sun. And so when these two very massive objects spiral together and eventually collide, they release a flood of energy and create a phenomenon referred to as a kilonova. The unusual event that we know today seems to produce huge amounts of heavy metals, and especially gold and platinum. But normally we expect these events to happen in somewhat active or busy regions of a typical galaxy, so basically inside some kind of a star-forming region, or a location with a lot of stars where some of them might have produced neutron stars. And so normally we expect this from a center of a medium or a large galaxy. But this event was different. When combining the observations from the X-ray vision of the Chandra X-ray Observatory with the sensitivity of the Hubble Space Telescope, researchers realized that this was not in a galaxy itself. As a matter of fact, it almost appeared to be in the middle of empty space, or at least it appeared this way at first, which by itself would have been extremely unusual, as we don't really expect neutron star collisions in between galaxies. Yet nevertheless, here this appeared to be offset from any major galaxy, and at first appeared to be in the empty space, but the observations from the Hubble actually showed us where exactly this was. And so essentially here, by focusing on this region and by trying to distinguish different objects, researchers definitively confirmed that this was actually a part of the galaxy. But in this case, it seemed to represent its tail, and specifically the tidal tail, that was surprisingly at least 600,000 light-years long, representing this very long stream of gas that escaped the original galaxy, with gas and stars stripped away during a massive collision between a galactic group hundreds of millions of years ago. And in this artistic representation, you can kind of see how this galactic merger seems to have happened, which is why this is now referred to as the collision within the collision. And so based on these observations, researchers can now figure out exactly what happened. And so first of all, this was obviously not a normal galaxy anymore, because this was a galaxy that was now tidally extended and contained a very long tail. And more importantly, it was very likely the galactic merger that then triggered a massive wave of star formation inside of this gas stream. And this very likely produced a lot of very massive stars, and in many cases in binary systems, with many of these stars eventually going supernova within the last 100 million years. And because some of them were in binary systems, here in at least some cases, the final product would be something like this: 2 neutron stars produced by massive supernova. And so here, based on the calculations, scientists believe that approximately 700 million years ago, a pair of supernova gave birth to these 2 orbiting neutron stars that at first were pretty far away from each other, but eventually, over 700 million years, spiraled closer and closer and closer, until one day they finally merged, producing the kilonova. And so definitely a pretty elegant explanation, and definitely an explanation that kind of makes sense once all of these additional observations have been conducted. But for astronomers, this, as I mentioned, does actually explain several things, and basically solves several mysteries. Because this is such an unusual location, it finally explains to us why sometimes we see these explosions without any potential host. And that's because for many years astronomers have actually witnessed these GRBs, or these very powerful explosions, coming from locations that seem to have nothing there. But it turns out that even though it appeared to be in the middle of nowhere, many of these bursts very likely did actually have a host galaxy, but would only be seen through powerful telescopes like the Hubble or the James Webb. And so in this case, the tidal tail, or the location where these explosions happened, seem to be invisible because they're basically kind of diffuse. And for this particular explosion, this burst seems to have happened in a relatively tiny dwarf galaxy that was also buried inside of this tidal stream. So this was actually one of the leftovers following the galactic collision. Here's the actual image from the Hubble Space Telescope showing us where it seems to be located. But then there's the second mystery. The mystery of a lot of complex elements, and specifically heavy metals, in between galaxies. And well, first, today we know that neutron stars, as they merge, generally produce what's known as the R-process nucleosynthesis, a very powerful reaction that causes many different lighter elements to start converting into heavier elements. And so generally this mechanism seems to be responsible for forming at least half of the atomic nuclei heavier than iron. And so gold, platinum, but even things like uranium. But at the same time, for many years, astronomers have been detecting gold and platinum in locations very far from the central galaxy. So basically in places where none of this should be possible, mostly because there's nothing here to make it. But this particular GRB definitely shows us that mergers can happen on the outskirts and effectively act as a kind of a seed for many of these remote regions, enriching them in a lot of heavy elements and of course heavy metals. And so this was basically an official proof that neutron mergers and kilonova can actually happen in locations where we never expected them. And not so long ago, actually just a few months ago, researchers from the Max Planck Institute for Gravitational Physics created one of the most complex computer simulations trying to actually understand exactly what happens when neutron stars collide. And so essentially here they tried to look at this event from start to finish. And in this case, this very complex computer simulation, involving over 100 million CPU hours, but actually only simulating like 1.5 seconds of real time, revealed to us what seems to happen during these collisions and what all of this produces. And so in essence what you're seeing here is something that happens in just over 1 second. with this collision leading to a rapid collapse of two separate neutron stars into a slightly more massive black hole that then, as you can see here, starts to form an extremely powerful jet. The jet that eventually powers the entire gamma ray burst and results in these very powerful emissions visible from billions of light years away. But once again, all of this only lasting for like a second or so, until it shuts down completely and until this becomes just a silent black hole. Naturally though, these events also usually result in very powerful gravitational waves that have been detected previously by the LIGO facility, although as far as I know, this particular event was not detected. And well, right now this is actually one of the most important simulations when it comes to neutron star collisions and will hopefully help astronomers understand some of the future signals, especially once we discover more gravitational waves that seem to have come from neutron star collisions. At the moment, only a handful has been discovered so far. But as it stands, this is definitely one of the most exciting neutron star collisions detected so far, and basically reminds us that even in this destruction, there's actually a kind of a catalyst for creation. In this case, creation of heavy elements that will probably end up on various planets out there, and that are obviously inside of our bodies right now. A lot of the heavier elements we have did actually come from neutron star collisions billions of years ago. Not to mention the gold ring you might have on your finger was also very likely formed by one of these events. But when it comes to galactic mergers and the future of these events, we know that the Milky Way galaxy may experience something similar billions of years later. And so as the Milky Way galaxy starts to merge with its partners, there's a very high chance it will also produce these tidal tails, and in the next 5 billion years, it may also start forming these neutron star pairs, eventually triggering a new round of star formation, more neutron star collisions, and more enrichment of the universe around us. Or at least that's what we can kind of assume based on the observations from this galactic merger and based on what we know about our own galaxy. It's now been approximately 14 years since the original discovery of FRBs, or fast radio bursts. Very strange, unexplained radio emissions, very powerful emissions, that at first scientists thought might actually come from planet Earth, from things like maybe satellites or even microwaves. But as the time went on, and as more and more have been detected, along with some really thorough observations, scientists realized these are actually coming from very distant galaxies and seem to be coming from pretty much everywhere, suggesting that these are powerful events with a single burst equivalent to the amount of energy our Sun produces in approximately 1 year. But a single signal here is always shorter than 1 second, which is why they're known as fast radio bursts. And because they're so short, and because these are radio signals coming from really far away, it's been suggested that they're probably formed by something relatively small. Basically, for the light to travel in such a short time, this has to be less than 300 kilometers in size. So possibly some kind of a black hole, maybe a neutron star. But even after 14 years of research, there is still no clear explanation, even though one of these events has been detected right here in the Milky Way galaxy. And so, hello wonderful person, this is Anton. Today we're going to discuss some of the recent discoveries in regards to FRBs, and actually 2 potential explanations to how they form somewhere out there. And both of these new studies decided to focus on 2 most famous FRBs, the closest one to us, and the one that's known to repeat quite a lot. And this is based on a very famous neutron star, specifically a very famous magnetar, known as SGR 1935 plus 2154. Here's roughly what this location looks like in radio light, and here's the same observations done with X-ray telescopes. And so a few years back, as we've discussed in one of the videos right there in the description, completely by accident, researchers studying this magnetar discovered that it seemed to have produced a fast radio burst. And not just 1 or 2, it produced quite a few. And during this time, this object was observed by X-ray telescopes before and after the event, obviously with the main purpose of understanding how all of this forms. And so in October of 2022, and even several times before that, it produced a few fast radio bursts, captured by several telescopes, such as NASA's NICER, located on the International Space Station. And interestingly, one of the main discoveries in this case was the fact that something happened to this magnetar before and after this FRB. In essence, it experienced what's known as a glitch. And this is a term used in astronomy to talk about neutron stars that for some reason sometimes accelerate just a little bit when it comes to their rotation. And so in this case, this magnetar suddenly started spinning just a little bit faster and did this twice. And in between these two glitches, that's when this FRB seems to have happened. And I guess here it's kind of important to understand exactly what we're talking about. We're talking about something that has a mass of the Sun, technically even more, but is smaller than the city of New York. And so this extremely dense, really massive object, spinning really fast, if it accelerates just a little bit in its rotation, whatever happened here must have involved a tremendous amount of energy. And this particular magnetar spins 3.2 times per second with its surface velocity of approximately 11,000 km per hour, or approximately 3 km per second. But suddenly, within just a few minutes, it changed that velocity by just a little bit and did so twice. And whatever caused this must have been super powerful. But in between these glitches, what surprised the scientists behind this recent study is that this magnetar also slowed down in approximately 9 hours. Or basically it slowed down much faster than ever observed around any neutron star. It's not entirely clear why, but because of this extremely fast decrease in rotation speed, it's believed it resulted in the release of these very fast radio bursts. Basically it had to somehow shed all of this energy, and this was done through radio burst emissions. Now normally, in a typical magnetar, when it suddenly accelerates, or when it experiences this glitch, it usually takes weeks or even months to get back to its normal speed. Here though, it only took 9 hours. And though obviously this was a very surprising discovery, and currently does not have a very specific explanation, it shows us that we still know so little about magnetars, and they're still full of mysteries. These are obviously some of the most powerful objects in the entire universe, representing some of the most extreme neutron stars with a ridiculously powerful magnetic field. Fun fact, or I guess a scary fact, if you come really close to one of these objects, the power of the magnetic field is actually going to disturb a lot of chemistry in your body, and even the atoms inside your body are going to become ripped apart by ridiculously powerful magnetic fields. So yeah, death by magnetar is maybe not the way to go. But I guess back to FRBs. So what the scientists now learn about this is that it seems to be the result of whatever is happening inside magnetar, and specifically the very extreme conditions formed by quantum mechanics when things become ridiculously hot, very pressurized, and quantum in nature. Today, based on what we know about quantum mechanics and experiments with extreme matter, scientists believe that a typical neutron star consists of at least two states of matter. We have a kind of a solid surface that's basically crushed by the gravity so much that even a single mountain here cannot be taller than just 1 millimeter. And then we have a kind of a quantum superfluid inside that potentially resembles a typical fluid in the way it interacts with everything else. But because these objects spin, here the researchers explain some of these effects as essentially, well, I guess a fishbowl spinning around. Because of the sloshing of the liquid inside this object, sometimes the liquid can spin just a little bit faster than the surface, meaning that the surface, the crust, or the fishbowl's glass has to somehow catch up. And that's when the glitch occurs with this extra energy released in the process. And so basically the internal liquid and the external surface, solid surface, do not really spin at the same velocity at all times. But when they become out of sync, something has to happen in order to release the energy from the inside by delivering this to the crust, which might occasionally even crack the surface, to some extent resembling a kind of a ridiculously powerful volcanic eruption. And so by losing this mass very suddenly, it causes the object to spin just a little bit slower, thus explaining this rapid deceleration, but also possibly the sudden release of fast radio bursts. At least that's the explanation we have for now. It's still super preliminary and there's no actual evidence, just the theory behind this, but naturally by studying a lot of superfluids and interaction of superfluids with a lot of other extreme matter, we might be able to come to a conclusion of how this works. And naturally one day, this could potentially be used in practical way right here on planet Earth. How? I don't know. Somehow. I mean, we've discovered ways to use other stuff, so this might also get used somehow. My guess is some kind of a super cool scanner, like a super advanced MRI or something. I don't know. Anyway, moving on. So that's our first observation from the closest FRB to us. But then we have the most famous one, or I guess the one that's repeated the most. This is a really famous FRB detected in 2012 known as FRB 1211-012, and it became the first ever known repeated FRB that basically happened many times. it's already produced over 1,000 bursts, suggesting that whatever is happening here is happening over and over again. And in the last few years, scientists even identified the small dwarf galaxy where it's probably coming from. It seems to be at a distance of about 3 billion light years away from us. So yeah, despite the distance, we still see it really well. And so in this recent study, the researchers decided to analyze approximately 1100 bursts from this FRB in order to discover some kind of a pattern to then try to explain what's going on here. And though at first it all seemed kind of hectic and potentially unpredictable, here by combining the results in certain ways, they were able to discover two separate periodic patterns. One seemed to repeat every 157 days, and one every 4.6 days, basically suggesting that maybe something was actually orbiting with this FRB, thus producing these unusual observations. Although I guess a bit of a caution here. A bit of a follow-up from some other scientists suggested that maybe here the analysis conducted found patterns that might not really exist. So all of this is still super preliminary. But nevertheless, here we go. So what's the explanation? Well, as you can imagine, they suggest two separate objects. First, there seems to be some kind of a star with a 157-day orbit that once in a while disturbs the neutron star, potentially causing these glitches, and thus causing the release of powerful radio energy. That by itself is not super surprising. But it's that second result that is surprising. Here they actually propose that this object might have a planet orbiting every 4.6 days. And it's that planet that's causing the second signal. A planet that orbits at about 5% the distance of Earth to the Sun, and a planet that's potentially bombarded with a ridiculous amount of super powerful radiation. Here we're talking about gamma rays, X-rays, you name it, it has it. With scientists even suggesting that if this planet exists, it's probably supercharged with a lot of these particles and possibly is always filled with some kind of a lightning or some other unusual effects. Likewise, if confirmed, this would also be one of the most distant planets ever discovered, basically at a distance of about 3 billion light years. But the question is, does this actually make any sense? Well, it kinda does, and for reasons that you see right here. This image was produced in regards to a different discovery. What you're looking at right here is a planet, a known planet, around a neutron star. As a matter of fact, these three planets are the first planets to be ever discovered in the entire galaxy back in 1992. Today they're known as pulsar planets, but in a nutshell, because of slight deviations of pulsations from this neutron star, back in 1992 and 1994, Polish astronomers discovered that there are three separate planets here, and they all seem to be terrestrial, potentially resembling something like this. And more planets like this have been discovered in the last few years, but this one was obviously the first. You can learn about this whole system in one of the older videos, somewhere in the description. But the reason I'm showing you this is basically because, one, we know neutron star planets definitely exist, and so there's actually a slight chance that this is exactly what's causing the unusual radio emissions from this neutron star as well. But I guess two is that we can technically use this system to possibly see if we can detect similar emissions, or basically similar fast radio bursts, in order to basically test this hypothesis. Now right now nothing like this has been done, and as far as I know this system has not been studied for a very long time, but I think it's maybe a good time to take a look at it once again. It's roughly around 2300 light years away from us, and here this is not a magnetar, it is actually a pulsar, spinning 161 times per second. And so I guess technically, because this is not a magnetar, we might not see exactly the same emissions, but we might see something similar. And also interestingly, as far as we know, this particular pulsar was actually a result of a collision between two different white dwarfs, which is why it's spinning so fast. And so this whole system has a very intriguing and somewhat unusual origins. But more importantly, it might help us solve the mystery of the FRBs, or potentially help us discover even more mysteries, I guess. But anyway, the whole point I'm trying to make is that it's about time someone took a look at these particular planets once again, especially using some of the most modern telescopes. In the last couple of years, several major studies started to report discoveries of somewhat unusual cosmological signals. Strange blinking objects scattered across the Milky Way that were not very easy to explain. And they were actually discovered completely by accident because of the advances in radio astronomy. Now in the past, many different blinking radio objects have been discovered as well, but these were usually extremely fast, and today we refer to them as pulsars. Essentially, pulsating neutron stars, whose spinning mechanism seems to produce these very specific radio emissions. But here this was something entirely different. The first such object was only discovered in 2022, and this was like nothing we've seen before. Here, in some sense, this was also a pulsar, but it was basically in slow motion. At 4,000 light years away from us, this unusual signal was actually producing 30 to 60 seconds of radio emissions every 18 minutes. And it was reported in this study by Hurley Walker and the team you see right here. You can also learn more about this in one of the previous videos in the description. And though even back then there was barely any explanation, it didn't take long to discover the second object, 15,000 light years away, emitting radio signals lasting for 5 minutes with a pulsation of 22 minutes. This was discovered by the same researcher and the team you see here just a few months later. And well, eventually, Natasha Hurley Walker that you see right here continued to discover more and more. For example, here's another one discovered just 1 year later, 5,000 light years away, 30 to 60 seconds long, every 2.9 hours, with at least 10 such objects now known as of 2025. And though it's still unclear exactly what these are now known as LPTs, long period transients. So I guess kind of like pulsars, but just super slow. But even after all this time, there is really still no exact explanation. Because these are completely new to us, nobody has any idea what's going on and how these signals are generated. Nothing like this has ever been seen before, nothing like this has ever been predicted, and these radio signals are just way too slow to be neutron stars or magnetars, and way too powerful to be anything else. Also, they look just a little bit too natural and too unpredictable to be aliens. And so basically here we're stuck with these new, strange radio mysteries across the entire galaxy. They seem to resemble pulsars, but pulsars with signals at least 1,000 times longer. And because of the way we know pulsars generate these signals, it would be impossible for them to spin so slow. Here we're talking about rotation in hours or even in days. Not to mention that these are really strong signals, suggesting that whatever this is, it has to be super powerful. But so far the majority of these discoveries basically came from this telescope. This is known as ASCAP, Australian Square Kilometre Array Pathfinder, which in the last few years produced some of the most incredible radio maps of the entire night skies. We've actually discussed a couple of them in some of the videos in the description, and one of them still kind of blows my mind. It's literally this three-dimensional interactive map you see right here, where you basically see a bunch of objects, but all of them only visible in radio light. And here you can actually click on individual objects to see exactly what they look like as a radio emission compared to what we're usually used to. There's a few other maps we've discussed before in some of the videos in the description, but in essence, because of these discoveries and because of these new maps, or technically because of these new surveys, there was now a lot of new data that was previously unavailable, including data on various pulsating objects that were actually pulsating relatively slow. And this is how some of these LPTs were discovered initially. But now we have a new discovery that completely by accident became even more exciting. Here this is an object 15,000 light years away that you can kind of see right here. ASCAP J1832-0911. It seems to emit 2-minute pulses every 44 minutes, which essentially makes it another one of these LPTs. But when ASCAP was collecting data about this object, completely by accident, it was also observed by Chandra. And as you might know, Chandra Space Telescope can only see things in the X-rays. And here, it also recorded very unusual pulsations that seem to correlate directly with radio signals. You can see both radio signals and the X-rays in this image. And to astronomers, this is a really strange behavior. These somewhat methodic radio signals, with every pulse produced with such an unusual regularity, and visible in both radio light and X-rays, is actually even more difficult to explain, especially because the pulses coming from this object are extremely bright, producing a lot of luminosity in the X-rays and in radio waves. But on top of this, based on these observations and further analysis, researchers established that this has to be a somewhat compact object, basically relatively small in size, and it seemed to produce no emissions before November 2023. So it actually only became this way extremely recently. Like here we're just talking about under 2 years. And that's super bizarre. For example, every single pulsar known to us has been active and has been pulsating for as long as we've known them. And they are expected to pulsate for many years. Normally, for a typical pulsar to stop producing radio signals, has to slow down its spin just enough for the magnetic mechanism to no longer produce enough radiation. And normally it's expected to happen maybe within 10, but usually 100 million years. And also they're unlikely to just start like this out of nowhere. Yet here this object defies all modern theories. And as always, you can read more about this in the study right here. Detection of X-ray emission from a bright, long-period radio transient. A study by Z10 and the team you see here. And based on previous models and previous explanations, right now not a lot of them actually match. For example, before it was proposed that maybe these are extremely magnetized neutron stars, or maybe white dwarf pulsars, or possibly even binary systems with a white dwarf and some kind of other star that seem to produce these emissions because of very slow spin or because something is orbiting around them. But these particular models did not predict X-rays. And though X-ray emissions could be possible from ultra-long period magnetars or some unique white dwarf pulsars as described in this study, none of them produce radio signals and X-rays in such an unusual synchronized way, and none of them have these very long, very powerful emissions. And so right now there's really no clear idea exactly what's happening. For example, here you're seeing one of the previous explanations that involved some kind of a pulsar striking a star that then produces emissions from its surface, while we also observe emissions coming from the pulsar as well. But even these theories do not fully explain what we're actually seeing. And so right now the assumption is that this is an entirely new type of physics when it comes to stellar evolution and stellar objects. Especially because even though the radio and X-ray pulses seem to resemble a magnetar, the overall behavior and the emissions are not consistent enough with magnetar activity. Or just to rephrase this, the radio and X-ray emissions look nothing like what we usually see from a typical magnetar. And if this is a white dwarf, and a white dwarf that's spinning super slow, it actually seems to be several million times more powerful than any other white dwarf seen before. Not to mention that usually white dwarf emissions are also polarized. Here the radio light is very different. And so right now one of the potential best next steps is to try to observe previously detected LPTs and try to see if they also emit something in the X-rays and maybe some other wavelengths. If scientists discover that all LPTs produce X-rays and radio emissions, this might definitely point at some kind of a new stellar object and some physics we've never really considered before. Or maybe this is just a very unique object and something very different, never before seen in the entire galaxy. In this particular case right now, this is a very energetic object, producing just as much energy as a typical super flare from a very active star. In other words, every single one of these emissions is just as strong as an extremely powerful flare coming from some of the most active stars out there. But because it's only started recently, and because in the last 6 months the X-rays and the radio emissions seem to have actually died down a little bit, seems to suggest that whatever this is, it's not going to be permanent, and it seems to be only affecting this object on human timescales. So for all we know, in the next few years, it might disappear completely. And that means that we might not have enough time and not have enough observations to determine what this is. What is certain though, this is definitely like nothing we've seen before, and right now seems to be one of the most unique objects in the entire galaxy, and technically the entire universe. A strange radio and X-ray pulsator producing signals every 44 minutes. Something we'll discuss again once there are more discoveries or more clarifications, or once someone proposes something concrete that explains all of these bizarre pulsators once and for all. Hello wonderful person, this is Anton, and today we're going to discuss a relatively new study that focuses on one somewhat unusual proposition. The proposition in regards to neutron stars. And here, the researchers behind this study make a pretty strong argument for the existence of unusual, almost like atmospheric clouds orbiting around neutron stars that are actually made out of something entirely different. They're made out of axions, hypothetical particles proposed as an explanation for a lot of mysteries in physics, including dark matter. And so in other words, the researchers behind this study suggest that pretty much most neutron stars out there contain unusual atmospheres made entirely out of dark matter particles. And the argument they make is pretty strong. And so let's talk about this in a little bit more detail, but I guess let's start with axions. So what are they, and why do so many scientists believe they exist? And well, axions were initially proposed by the famous Frank Wilczek, an American physicist who won the Nobel in 2004 and who's essentially an expert in everything when it comes to particle interactions. And sometimes around 1978, he proposed that in order to solve one of the biggest problems in physics, the strong CP problem, the problem that stems from the observation that the strong force, one of the fundamental forces, preserves charge parity symmetry, CP symmetry. And this is despite the fact that nothing actually requires it to do so. And so here the question was, why is CP symmetry respected when it comes to the strong force? Now I know this is quite a loaded question and quite a lot of information, but you can learn a little bit more about this in some of the links and some of the videos in the description. In essence though, the Axions offered an elegant solution to this puzzle and represented a super light particle with a spin of 0 that would suddenly offer the solution to this charge parity symmetry. But within just a few years, researchers realized that this can actually also explain a lot of other problems. These axions also appeared as an extremely common feature in the string theory, and they seem to arise in various extra dimensions as those dimensions become more compact. But much more importantly, in terms of this research, they also became the leading candidate for the explanation involving dark matter, the invisible substance that seems to make up most of the mass in the universe, but that seems to not really interact with anything except for gravitational effects. And so in this case, the axions could potentially explain a lot of things all at once. But over time, scientists realized that axions can also actually be affected by extremely powerful magnetic fields. Specifically, they can be produced in regions with extremely strong and varying electromagnetic fields, such as for example around polar caps of various neutron stars. Likewise, sometimes axions can be converted to photons, but photons with a lot of energy. And so when exposed to these very powerful magnetic fields, sometimes we expect these axions to basically become X-ray photons. And not so long ago, we've actually discussed one of these potential detections coming from extremely famous neutron stars known as the Magnificent Seven. But so far this detection has not been confirmed by others. Nevertheless, it was still there, even though it was kind of preliminary. And so essentially to discover these axions, neutron stars have always been the main target. They created the perfect environment. As a matter of fact, some of these neutron stars, especially Magnetars, would basically be axion factories. They would be generating so many of these axions that technically, even using modern telescopes, we should be able to detect them eventually. But this was obviously still a hypothetical proposition and even a hypothetical particle. Nobody knew if they even existed. Nevertheless, even their name, axion, is basically a kind of a play on words. They're named after a brand of soap that's actually still available in the stores, and that's because their existence was really supposed to clean up the problems in physics. Problems with axions, problems with the strong forces, and the problems in the string theory. But because they're proposed to be extremely light in mass, they would be practically impossible to detect naturally. So we can really only find them by looking at interactions with something else, such as powerful magnetic fields. But neutron stars contain everything we need: extreme densities, extreme magnetic fields, and they're also small enough in size that everything around them kind of stands out. And so for several years, researchers basically speculated that many of these neutron stars should be spewing out axions left and right, but mostly by producing specific types of X-rays, which is essentially what the study by Bushman and his team was trying to describe back in 2021. But this new study that just came out by Dion Northios takes a slightly different approach. Here the assumption is that it might be easier to find axions that actually get stuck around neutron stars because they potentially form extremely dense clouds. In some sense, so dense that we can even refer to these as dark matter atmosphere. And that's because as a lot of these axions are produced, many of them get captured by the star's gravity and eventually get stuck in this orbit for possibly millions of years. And that's because these magnetic fields are so powerful, they can easily overproduce many of these axions that eventually get stuck for a long time. And even though some of them do escape, most don't. But if they don't actually do anything except for basically orbit around the neutron star, they would still be very difficult to detect. However, we know that neutron stars occasionally do go through certain changes. For example, a magnetar can shut down, reducing its magnetic field dramatically, which will very likely result in a massive axion escape and thus a sudden X-ray burst. But these events are kind of rare. There is, however, one event that's not rare, and we refer to these as pulsar glitches. And while approximately 6% of all pulsars known to us tend to sometimes accelerate their spin, which we refer to as a glitch, this has actually been explained as a type of a starquake, and it dramatically shifts the conditions around the star for at least some time. And that of course includes the magnetic field. And so during such an event, we do expect a sudden and dramatic shift of axions around the pulsar, which a lot of different telescopes we use today can technically pick up and identify. So for example, telescopes like LOFAR can monitor known pulsars for these transient events and then combine them with observations in the X-rays to find out if maybe we're actually detecting axions, or axions that turn into photons. And so basically in this study, scientists proposed a definitive way to identify these clouds and to obviously find out if axions really exist. Here the implication is that we have all of the technology needed, including all of the telescopes, to make these detections real and to potentially finally discover axions once and for all, and thus discover the dark matter. And that's because these axions, if they're real, should be producing these axion clouds around every single object that possesses high density and powerful magnetic fields. So basically pretty much every neutron star, and maybe even certain black holes, possibly even certain white dwarfs. And because this would be very dense environments that can be easily disturbed by minute changes in the magnetic field, even a tiny pulsar glitch should actually produce necessary results. And that's of course on top of some kind of a long-term signal that should be produced as a lot of these axions escape over time. And so in some sense there are two possible ways to discover if this is real, either by observing these glitches or sudden changes, or by discovering some kind of a long-term emission. And likewise, we could maybe even find something by studying various binaries, either binary neutron stars or neutron stars that have some kind of a different partner. So here we also expect different interactions, and thus different observational signals, something that's basically beyond predicted values. But in order to understand this, and obviously in order to discover and confirm this might require additional branches of sciences, including potentially plasma physics, that could provide explanation for how this neutron star cloud acts over time, and for how it seems to grow over time, eventually changing and becoming either denser or more compact. So basically this is just a first proposition and a first assumption, but it will obviously take years to see if this is actually true. In the last few weeks, for some strange reason, there's been a sudden surge of various discoveries pertaining to neutron stars right here in the Milky Way galaxy. At least 4 separate studies came out just recently, all 4 discovering things we never knew about neutron stars, or finding neutron stars in locations we never thought possible. And so in this video, I wanted to basically discuss some of these somewhat bizarre discoveries, talk about what all of this teaches us about neutron stars, and discuss why this is kind of important. But I guess the first question is, why exactly are neutron stars so important, and how can these unusual discoveries help us understand the universe around us? Well, one of the main reasons is because we actually have no idea what happens inside neutron stars. I mean, they are called neutron stars because at these pressures and in these extreme conditions, everything basically gets squeezed into neutrons. But as you go deeper and deeper, at some point, we actually expect something entirely different. Possibly some of the most extreme types of matter in the universe, which by their nature are going to help us understand exactly what's happening in the universe in general, and how the universe began, and of course what it was like in the first few moments right after the Big Bang. And that's because the internal structure of the neutron star does represent conditions extremely similar to the ones right in the beginning of the universe. But unfortunately, the current understanding of their structure is somewhat limited. It's mostly based on various studies involving astroseismology, or basically looking at various quakes and various glitches on these stars, combined with various mathematical models, mostly based by what's known as the equation of the state, which is essentially a theoretical model that describes physical processes that are supposed to happen inside neutron stars. But the problem is that there are a lot of these equations, hundreds, and actually possibly even thousands. And so right now nobody knows which of them is correct. But extremely recently, the scientists using Chandra X-ray telescope identified a few anomalous neutron stars that seem to be extremely cold for their age. And because of this unusual coldness, this basically disqualified approximately 75% of previously known equations of the state. In other words, we got just a little bit closer to possibly understanding what happens inside of them. And that's because 3 of these stars were approximately 100 times colder compared to several other stars of similar age. And that means that they cool down extremely quickly, involving a mechanism that can only be explained by certain equations of the state, which essentially disqualified a lot of previous assumptions. Then, in a separate study by using the NASA's NICER telescope, another X-ray telescope, but this one on the International Space Station, a different team of researchers focused on one of the closest neutron stars to us, the neutron star PSR J0437-4715. And because this star has a partner, a white dwarf, it actually becomes possible to measure precise emissions from this pulsar down to individual delays because of the orbiting object. And so the X-ray observations mixed with radio observations allow the scientists to visualize the surface of this particular pulsar extremely well. Here you're looking at various X-ray hotspots with these unusual magnetic poles, surprisingly, not exactly opposite each other. But because the star is so dense, it also produces unusual visual effects caused by extreme gravity. But I guess more importantly, it also allowed the scientists to work out the exact size and the exact mass of this object. 1.42 solar masses, 11.4 kilometer radius, which is really important once again for that equation of the state. It once again disqualifies quite a lot of different equations, thus taking us just a little bit closer to then working out the equations for pretty much all of the extreme conditions in the entire universe. And so these two studies take us just a little bit closer to understanding neutron stars. But the two other studies discover other things we obviously didn't expect. For example, in one of the recent studies by using ESA's Gaia telescope, the space telescope responsible for mapping the motion of various stars, here scientists discovered something else nobody thought was possible. Specifically, a unique binary system where a neutron star seems to orbit a star very similar to our Sun. And so why exactly is this surprising? Well, generally we know that there are a lot of binary systems out there, with some systems even being exotic, sometimes containing a black hole and a neutron star, or even both orbiting each other. But in many cases, we see their interaction because they usually produce a lot of X-rays and a lot of additional emissions, as the neutron star or a black hole absorbs a lot of matter and creates accretion disks and powerful jets. But there is one type of a pair that seems to be extremely unusual and also extremely rare. A neutron star and a Sun-like star, but orbiting really far from each other, usually at distances of several astronomical units, or basically the distance of Earth to the Sun or even farther. And here the researchers discovered 21 such objects, all found by observing miniature motions of the star as something tugs on it over a period of several months or several years. And so because Gaia is so sensitive, it was able to see these, thus allowing us to discover these practically invisible objects. And that's because in this case, these neutron stars are entirely quiet. They don't produce any emissions, they don't have any accretion disks, and they're unlikely to produce any jets whatsoever. And so here, a discovery of 21 such objects was really surprising. And one of the biggest surprises is really, we don't really know how these were formed. Mostly because the distances between them is really far. And that's because, in order to even produce a neutron star, you need to have a powerful supernova. And this type of a powerful event is expected to completely knock out the other star, basically sending both objects in completely opposite directions. Yet here we see that, I guess, at least in some cases, some of these stars seem to survive and do maintain close orbits that potentially last for millions and billions of years. Even though technically, there's currently no model that can explain everything here, and at the moment, all of this is just an assumption. But because of this discovery, these are essentially the first ever neutron stars discovered entirely by observing gravitational effects exerted on the partner object. Although here it's assumed that these are super rare. Based on this number, and based on the distance, researchers believe that only about 1 in 1 million of solar-type stars would contain a similar partner. Which means that the Milky Way galaxy might contain something like 7 to maybe 30 million similar star systems out of 400 billion stars in existence. And then we have our last discovery that's, I guess, even more strange. And this one comes from a very famous cluster, a globular cluster, that's already known to contain 39 separate pulsars, or essentially neutron stars, that pulsate in various frequencies. And this is a cluster known as Tarzan 5, an unusual cluster that seems to follow a somewhat strange orbit around the Milky Way, but also a cluster that contains the highest star density in the entire galaxy. Here there are more stars per volume than literally anywhere else. But most importantly, It's really the number of pulsars discovered here that seems to be strange. And for many years we've known that many of them seem to be really bizarre. They either have very eccentric orbits, or produce extreme effects, or even pulsate at ridiculous speeds. As a matter of fact, the record holder for the fastest spinning pulsar is also located here as well. You can see the name of this pulsar right here, and surprisingly, it was actually discovered in my university, literally when I was studying there. But back then, I had no idea it was discovered, and it didn't make any news anywhere. I don't think anyone in the university even talked about it. But that's beside the point. The point is that this right now is the record holder, and it spins 716 times per second. So yeah, that's actually kind of hard to imagine. Basically, imagine something size of a city, with the edges of that city flipping over and over 716 times every single second. That's basically it. That's how absolutely ridiculous this pulsar is. But in this new study, the researchers discovered 10 more, with some even more extreme and more bizarre. And in this case, all of this was discovered by tracking this cluster with various telescopes for several years. And so after 20 years of 2005 observations, the researchers were pretty confident they discovered 10 more objects. Now at least 2 of these discovered objects were binary neutron star systems. And these are super rare. Out of 3,600 known pulsars in our galaxy, there are actually only 20. And the thing is, when neutron stars become binaries, as they orbit one another, the way they interact causes them to start spinning faster and faster. And at some point, if one of the pulsars starts to also steal material from the other, it essentially forms a kind of a temporary millisecond pulsar. A pulsar that keeps spinning faster and faster and faster, reaching absolutely ridiculous speeds. And so one of the recent discoveries spins approximately 440 times per second, and is part of that binary system. On top of this, some of these pulsars had very eccentric orbits, basically with an eccentricity of a typical comet in the solar system. And this would naturally produce a lot of additional effects, many of which we still don't understand. And on top of this, they also discovered quite a lot of various black widows, or black widow pulsars, which are essentially neutron stars that are so close to some kind of a star that that star is slowly evaporating, turning into some kind of a different object, potentially a planet. And so 3 of these black widows were discovered as well, putting the total number of pulsars in 2005 at 49. So yeah, for some unknown reason, this globular cluster contains 49 known pulsars, and most of them are super weird, and are weird for very different reasons. But why this is so, and why this cluster and not really other clusters, that's something we cannot answer.
Hello wonderful person, this is Anton, and today we're going to discuss a discovery of yet another extreme neutron star, or technically an extreme pulsar, that almost beats all records, and more importantly, reveals an unusual mystery when it comes to the maximum speed of rotation for various neutron stars. Because here the researchers have recently discovered that this particular neutron star seems to spin 716 times per second. Or in other words, its rotation around its axis can be measured as 716 Hz, making this one of the fastest spinning objects ever seen. But intriguingly, its rotation is exactly the same as the other object discovered over a decade ago, and that by itself doesn't really make a lot of sense. And so let's discuss this particular idea in a little bit more detail, but first let's start with the actual system and why it's already kind of strange. Here's one of the older images created by NASA, illustrating what the system might contain. And so here, this unusual X-ray binary known as 4U1820-30, discovered inside the globular cluster NGC 6624, contains a neutron star and, surprisingly, a white dwarf. And because white dwarf is usually much smaller than any other star, here these 2 objects orbit really close. A single orbit takes just 11 minutes, making this an extremely short period and the only such system known to us out of all low-mass X-ray binaries. In a lot of other X-ray binaries, where we usually have either a black hole or a neutron star, they orbit around much larger stars, and thus a single orbit takes much longer. But the overall idea is the same. They basically capture the mass from the nearby partner, because the partner reaches what's known as the Roche lobe. Its mass starts to overflow into the black hole or the neutron star, with all of this inflowing mass then forming the accretion disk that eventually starts producing a lot of major emissions. But for objects like neutron stars, something else usually happens,
when they start to accrete so much mass. If they were not spinning very fast before, all of this mass then starts to accelerate their spin because of the transfer of the angular momentum. And so if a typical neutron star only spins 1 or 2 times per second, suddenly, through this process of accretion, they'll start acquiring a huge amount of spin, with current models establishing the limit to be approximately 350 rotations per second. And so for many different binary systems, where neutron stars start to accrete mass, they usually start rotating at least 350 times per second. But anything above that does become a little bit more challenging. And on top of all of this accretion, they also obviously start producing a lot of additional explosions as a lot of this mass accumulates and reaches critical values. And it's basically the case for this system as well. Just like so many other systems, it shows a lot of bursty behavior, with the accretion disk first producing a lot of X-rays, but then at some point producing an enormous thermonuclear explosion that in some cases can happen very frequently. In some sense, these are similar to your typical nova observed around white dwarfs. And so here, by conducting additional observations using NASA's NICER X-ray telescope on top of the International Space Station, researchers were essentially trying to study this pulsar by observing its thermonuclear explosions. But by accident, in one of the explosions, they detected a remarkable oscillation. And this oscillation usually means that the pulsar is spinning. And to be more exact, it allows us to calculate how fast it's spinning. And here the frequency was discovered to be 716 Hz. And so this 12 km in size object, approximately 1.4 solar masses in mass, and that's also about 26,000 light years away from planet Earth, was basically spinning as fast as we've ever seen. And so on top of this being the X-ray binary with the shortest orbital period, it was also the fastest spinning pulsar. Although just as a side note, these types of clusters usually contain a lot of pulsars, and this is one of several pulsars already known inside NGC 6624. But there is another much more famous cluster known as Tarzan 5. And back in 2004, something really exciting was discovered here as well. A team from the university where I was studying, from McGill University, discovered a pulsar that you can kind of see right here, known as PSR J1748-2446AD, that surprisingly spins at exactly the same value. In other words, we had two objects spinning at exactly same velocity, or with exactly same period. And honestly, this doesn't really make much sense, especially because these two objects are in completely different locations, have completely different age, and were even discovered decades apart. 2 decades as a matter of fact. And so because of this unusual frequency of 716 Hz, it kind of raises a question. Is this possibly the highest possible period for a typical pulsar to spin at? In other words, is this the limit? Now in terms of theories, the answer seems to be no. Based on, for example, different types of modeling, physicists predict that a typical neutron star would technically break apart if it spins 1500 times per second. So here we're talking about approximately double of what was just detected. But even spinning at 1000 times per second, neutron stars would lose so much energy by gravitational radiation that they would actually decelerate really quickly. And in this case, accretion of additional matter does not help them spin faster. And so in other words, gravitational waves from such a high spin rate would make them slow down really fast. And additional models even suggest that any frequency above 700 Hz would most likely produce so many gravitational waves that the overall spin would reduce with time. Yet here, we clearly have a case of something spinning at a little bit faster than predicted, 716. And not just one object, but two. So there's maybe a possibility that both objects reach the official physical limit. Although here I have to mention two more objects. One of them, with the name you see right here, 2 decades ago was also claimed to have a frequency of about 1122 Hz, so much higher. But a much more recent reanalysis from just a year ago actually discovered that it seems to be only spinning at 380 Hz, so just above that limit produced by the acceleration from the accretion disk. And so here this is unlikely to be the case to be a record fast spinning object. You can learn about this in one of the studies in the description. And then there's this object, PSR J0952-0607, that's classified as a black widow pulsar, or basically a pulsar slowly destroying its partner. I believe we've discussed this in one of the previous videos, somewhere in the description, that spins 707 times per second. so just a little bit slower than these two other objects, but much faster than anything else. And so these three objects, along with previous discoveries, basically present us with a kind of a limit for the rotation of the neutron star. There was actually a paper a while back that tried to create a kind of a distribution for the frequency of the spin, in essence discovering that at approximately 730 Hz, there seems to be some kind of an unofficial limit. In other words, we haven't really found anything above 730, with the fastest spinning objects clustering around the same frequency. And it could actually be much closer to 716 Hz for some unknown reason, because both objects seem to have that frequency, and so far we found nothing above that. And so here there might be some kind of an unofficial limit, possibly based on the combination of acceleration from the accretion, and potentially some other effects, and deceleration through the emission of gravitational waves. And this limit so far seems to be 716 times per second, or 43,000 revolutions per minute. And so at the equator, these objects spin at 24% the speed of light, or approximately 70,000 kilometers per second. And that's an absolutely mind-blowing value. And I don't think there's a way to imagine this or to even simulate this without setting my computer on fire. And the only way we can assume this is some kind of a limit is because both objects are extreme and both objects are spinning at exactly the same frequency. It's actually very difficult to explain why it's 716 and not something else. And for this system, because it's already so extreme, with the white dwarf so close and very likely losing a lot of mass, this is probably one way to explain why this neutron star is spinning that fast. And so once the white dwarf loses even more mass, and possibly at some point turns into some kind of almost like a planetary object, this system will potentially transition into something entirely different, with this white dwarf maybe even disappearing completely, or maybe being consumed by the neutron star, producing the last powerful explosion. But chances are that by studying this particular object, we might have some answers in the future, mostly because, despite distances, this is such an active system and produces so many explosions all the time that there is actually quite a lot of data to study for years to come. But chances are we're not going to know much more about this object until future studies, or until someone else discovers something else incredible about this system and potentially explains the unusual mystery of its very fast spin. But for now, you can check out the paper by Jai Zawal and his team in the link in the description below, and all of the other papers and other links should be there as well. Hello Info%, this is Anton, and it's time to talk about FRBs, or fast radio bursts, once again. Mostly because in just the last 2 months there's been some more updates and some more somewhat intriguing discoveries, potentially once and for all pinpointing one major source of many of the FRBs, solving the mystery of some of them. And so let's talk about these discoveries in more detail, and I guess let's start with one of the more recent studies that just came out. The study by Ines Pastor Marzuela and Jory van Leeuwen and the team from Netherlands. And here, by using the Westerbork Synthesis Radio Telescope, also known as WSRT, a very powerful telescope that contains 14 really large steerable antennae, researchers were able to discover over a dozen more FRBs, but more importantly, measured some of the properties in such a way that it actually allowed us to figure out what exactly potentially produced these bizarre radio emissions. But to understand this discovery, let's briefly go through the summary of previous discoveries and what we know so far. So most FRBs, most fast radio bursts discovered, all come from very distant galaxies. And though for every individual galaxy a typical fast radio burst would be kind of rare, because so many galaxies produce them, we actually see a lot of FRBs every single day. And prior to their discovery in 2007, which was actually done completely by accident, some of the most powerful radio emissions always came from pulsars, from neutron stars. And these can be visible up to 100,000 light years away, and sometimes even a little bit farther. But for the Milky Way galaxy, when it comes to fast radio bursts, so far there's only been one detection. This happened in 2020, and the video in the description talks about this more, but this location, SGR 1935 plus 2154, has been officially confirmed to host a neutron star, and actually to be more specific, a magnetar, and has now produced one FRB. Not very powerful, but an FRB nevertheless. And this was the first evidence we had that most of the FRBs extremely likely come from neutron stars. But understanding their origin is a completely different story. As a matter of fact, in modern astronomy, it's one of the main stories and one of the main scientific mysteries. And so in this recent detection of confirmed 18 FRBs, they actually all seem to show very specific properties of polarization and burst that we often observe in very similar objects such as pulsars and nearby magnetars. With just one exception, they're way brighter, or way more powerful. But they also all contain just a little bit of scattering, very likely produced by something around these objects, with that something potentially being a lot of gas. But every one of these FRBs was also slightly different from one another, which essentially suggests that whatever the source is, it seems to be embedded in different types of media and different types of, gas and different types of nebula, which makes them slightly different, produces slightly different frequencies and slightly different scattering, and would basically imply some kind of a nebular origin with something very powerful like a neutron star in the center. Which is exactly what we usually see in pulsar and magnetar systems as well, but once again with a lot less power. But intriguingly, around the same time, there was actually another really important study that discovered something very similar, but in a completely different way. Here they used something known as scintillation. And so in this study by Kenzie Nemo and his team, researchers took a slightly different approach. And it's the approach that we're all actually taught as kids when looking at the night skies in order to figure out if what we're looking at is a star or a planet. Now you might have already forgotten this, but back in the days I think most of us are told that if something is twinkling, twinkle twinkle little star, it is a star. Whereas if something is more or less stable and doesn't change much, it has to be a planet. So basically, a classic way of telling a star from a planet apart is that stars twinkle, planets don't. And that's because the light from both passes through our atmosphere. But because planets are actually a little bit bigger in size and technically appear as tiny disks, they don't flicker and their light appears more or less stable. This is based on the principle of light dispersion as it passes through the atmosphere. But for many different stars, especially really far away ones, because they appear as tiny dots, and the source in this case is a tiny dot, it starts to flicker, suggesting that the apparent size of the light source is actually the key factor when it comes to scintillation. And here an extremely similar principle can then be applied to very distant objects with light coming from very far away. And so for this other study, researchers looked at the scintillation of these FRBs as the radio waves traveling away from them move through various gas inside galaxies and through various interstellar medium. And in this case, if the object it's coming from is really small and very distant, we actually expect more scintillation or more twinkling, except that in this case it appears as radio twinkling or radio scintillation. And based on the analysis of a repeated FRB known as 2022-1022A, the FRB detected in 2022, researchers were able to constrain the overall size of this object, or the source of the FRB, providing very important evidence that the emissions in this case have to come from some kind of a magnetosphere or an extremely compact region of a very compact object. Or just to rephrase this, the only way this scintillation or this twinkling could be produced is only if it came from a very compact point within about 10,000 kilometers of a highly magnetized source. So that's basically smaller than planet Earth. And so this FRB has to have come from a super magnetized region, with the only object that's able to produce anything like this being Magnetar. So in this case, this study definitively confirms that at least one of these FRBs also came from a magnetar, just like in the Milky Way. And though some of the previous studies suggested that maybe this is actually created by something much farther away from the object, and is possibly the result of some kind of a shock wave or a massive cloud really far from the star, here this observation confirms that it has to come from the magnetic environment of an extremely compact object, and also very close to the source, which means that a lot of these FRBs are potentially generated right above the surface of the magnetar through some somewhat mysterious means. The actual process of production is still not understood, but there's at least one previous video that goes through some hypothetical scenarios. One of them involves swallowing a planet. But intriguingly, once again around the same time, there was actually another study that potentially created a bit of a problem for a lot of these explanations. And here this was a study that focused on trying to figure out where exactly a lot of these FRBs came from. So for example, by looking at something inside the galactic arm, like in some of the previous detections you see right here, it might be the result of a magnetar once again, because magnetars, in a nutshell, are just extremely young neutron stars. Neutron stars that are usually a few hundred or a few thousand years old that will eventually quiet down and become something else. We do expect these objects in very active star-forming regions and in various galactic arms. But it looks like, according to the new study, not all FRBs come from regions where young stars could exist. And so in a study we briefly discussed previously, one of the FRBs was discovered in a very bizarre place. This was a study you see right here, and we've briefly talked about it last time. But here this was first of all a quiescent galaxy that was not producing new stars as fast, a galaxy about 2 billion light years away from planet Earth, also an extremely luminous and a very massive galaxy, actually the most massive galaxy to produce an FRB so far. But more importantly, as you can see from this image, it came from the halo of the galaxy, 130,000 light years away from the center. And in this region we don't expect a lot of young stars, and actually expect a lot of ancient stars, for example inside globular clusters. Now in the Milky Way galaxy, inside a globular cluster, most stars are usually billions of years old. And so in these locations, we don't really expect to find magnetars. But here we had an FRB 2024-02098 that already produced at least 21 additional pulses in 2024 alone, and is most likely going to be producing more this year. Which basically suggests that maybe not all FRBs come from these locations with young stars, and maybe not all FRBs are produced by magnetars. But that second proposition didn't really make a lot of sense, because here the emissions still resembled everything else, very magnetized, coming from a compact region, and so it did actually suggest a magnetar after all. And the question was, so okay, what can be possibly happening here? Over 100 FRBs so far have been proposed to have formed as a result of a magnetar. They all seem to have very similar emissions. But that requires a core collapse supernova. Essentially a massive young star going supernova, leaving behind a neutron star, which then becomes a magnetar. But in the past there has been a proposition that magnetars might also form in different ways, and more importantly, in ways involving collisions. And so if this is some kind of a globular cluster containing ancient stars, it might also contain a lot of white dwarfs, just like in clusters around the Milky Way. And if there's a merger between two white dwarfs, or a white dwarf and a neutron star, according to at least one study we've discussed previously, there is actually a chance it might turn into a magnetar as well. Chances are that a lot of magnetars are formed in a very similar way, and colliding white dwarfs, in some sense, could also be some of the biggest sources for these bizarre radio emissions. And intriguingly, something very similar was also found around this galaxy, Massey 81, just 2 years ago. A very similar fast radio burst coming from a region that's outside of the galaxy, with extremely similar emissions, suggesting a magnetar. So basically these new discoveries potentially suggest that some magnetars form in ways we never imagined, or I guess more accurately, point at the fact that we have no idea how magnetars really form. We just know that they exist, we know they're very powerful and contain ridiculous magnetic fields, and we know that they seem to be responsible for fast radio bursts, at least most of them. But because this is still an active mystery, and a mystery that does not have a final conclusion yet, more observations are required in order to find more evidence and in order to have even more explanations. So you might have heard of alchemy, an ancient tradition whose main goal was to find a way to transmute things or transmute substances from one to another, with one of the primary goals for many alchemists being the transformation of base metals, like for example iron and lead, into a much more precious state, such as for example gold, which alchemists consider to be the highest form of matter. And while for many centuries alchemists searched for different ways to transform matter, and many of the early aspects used in alchemy eventually gave way to science we know today. But the reason I wanted to start with alchemy is because in the last few years, researchers have actually now figured out what creates gold in the universe, or essentially found several different mechanisms that actually do turn things like iron into gold. Here this is only possible in extremely powerful events that we're going to be discussing today. And so, hello info person, this is Anton. In this video we're going to discuss some of the most recent discoveries in regards to how gold seems to be produced in the universe, and mostly based on recent studies that actually solved some of the older mysteries, revealing that gold can be created in a lot of different ways we never expected, or I guess revealing these alchemical processes in the universe itself. And here this is kind of important because up until a few years back, up until I guess 2017, it wasn't entirely clear how gold was produced. For example, we know that various types of supernova seem to be responsible for producing a lot of heavier elements through the process of nucleosynthesis, with many observations of supernova remnants revealing actual elements being dispersed from the center. But it was really in August of 2017 that researchers finally confirmed how the majority of gold seems to be created. Here, by using some of the most advanced telescopes combined with the observations from LIGO, scientists finally discovered a gravitational wave that was also correlated with a major explosion. And specifically, this was a merger of two neutron stars that resulted in an enormous kilonova, where approximately 12 hours later, several telescopes were able to identify the explosion and observe the materials. This was approximately 130 million light years away from us, but it was close enough to observe exactly what was produced. And so this enormous energy resulted in the production of gold, along with several other heavier elements, suggesting that energy in this collision was powerful enough to transform iron and a lot of other lighter elements into much heavier elements through what's known as the R process, also known as rapid neutron capture process. The process of rapid capture of neutrons by a lot of different atomic nuclei that results in the production of much heavier elements. And so here, for days afterwards, by observing the infrared emissions, researchers discovered definitive fingerprints of several different elements whose origin was previously unknown. We've actually discussed this in more detail in one of the videos in the description. And so here, basically, for the first time ever, humanity witnessed alchemy of the universe itself, matter turning into gold, with this one single collision creating an enormous amount of it, approximately 10 masses of planet Earth. All of this was done in just mere seconds. But following this event, on August 17th of 2017, researchers continuously looked for other events, and specifically other additional events that can actually result in this R process that could explain other heavy elements or other gold. Because based on the predictions of this kilonova, there is just not enough of them to produce all of the gold we seem to be observing, suggesting that the universe very likely had other alchemical means. Okay, I really should stop calling it alchemy, because here we're really talking about our process, an actual scientific process that we can even recreate in a lab. And so not so long ago, in a separate study you see right here, researchers also speculated that it's quite possible that some other events, and specifically collapsing stars that end up producing black holes, could also result in the R process producing a lot of materials. And so things like gold, silver, and even uranium might actually be formed by extremely young, newly formed black holes that contain an accretion disk of a very specific size. And that's because in these conditions, the accretion disk also seems to encourage R process, causing a dramatic enrichment of neutrons in various elements. But because this process has to happen extremely fast, here this could only happen in certain accretion disks. They basically had to have a specific shape and a specific mass. And so, for example, during a collapse of a star that usually produces a baby black hole, it usually ends up having an accretion disk containing a lot of really hot material. But here at the same time, we get a lot of neutrinos, which result in nucleosynthesis happening in mere milliseconds. And so a black hole of a certain mass and a certain spin, with a certain mass of accretion disk, can occasionally have just the right conditions to suddenly start producing a lot of heavy elements, with the most important factor being the mass of the disk. A much more massive disk will obviously result in a much higher R process and the formation of more elements, but if it's too high, the neutrinos end up being recaptured by neutrons, thus hindering the R process and thus decreasing nucleosynthesis. And so basically here, in order to prevent certain types of radioactive decay, the accretion disk had to reach a certain balance. In their simulations, this usually happened with a disk with a mass of about 1 to maybe 10% the mass of the Sun. And in those conditions, these particular systems became extremely prolific at creating gold, or technically many different heavy elements. But in this case, it's obviously unclear how this gold would escape the system, and if it's even going to survive being swallowed by a black hole. Now, technically, it could escape through the black hole jets, or possibly by being expelled in some other way, but because all of this is based on modeling, right now this is more of a hypothetical concept. But the most recent paper that was just released is not hypothetical, and actually did discover a completely new way to generate gold in the universe. And this time, this is based on an older mystery of a very strange explosion detected in 2004. And you can even read about this in one of the older articles by NASA, or in this much older study by Palmer and his team. And in essence, back then, this was one of the most powerful flashes detected in the night skies. An extremely powerful flare that lasted for a few seconds and seemed to be coming from our own galaxy, from approximately 50,000 light-years away from us. And well, within just a few weeks, it became pretty clear what this was. This was a very powerful flare, but a flare coming from an extremely powerful magnetar, a mysterious type of a neutron star that we're still trying to understand. And so this magnetar produced such a powerful flare that it became visible from really far away, suggesting that it released just as much energy as the Sun in approximately 1 million years. Except here, all of this was in just a few seconds. And though additional flares have been discovered around other magnetars, here there was actually another mystery. Approximately 10 minutes afterwards, there was a second, much smaller signal. A signal that was not really explained at first and was eventually forgotten. And now, 20 years later, researchers finally found an explanation for what happened, providing specific details and explanations for what exactly occurred and why there were actually two signals. Now, first of all, the initial flare was most likely the result of some kind of a major reshuffling around the magnetar, such as, for example, some kind of a starquake. And well, according to Anirudh Patel and the team you see right here, during extremely powerful flares from magnetars, there should be enough energy to initiate our process once again converting lighter elements into something much heavier. In other words, here there was actually a prediction that a magnetar, in theory, should be also able to produce gold if the flare is powerful enough. But the thing is, up until recently, this was just a prediction. There was no actual evidence. And that's until they started to go through some of the older data, and that's when they discovered that second signal from 2004. And here researchers quickly realized that all of this seems to fit. First of all, the signal was never explained, second of all, it seemed to fit their model precisely, and third of all, it provided an important solution to the mystery of missing gold and missing heavy elements. And so it looks like they discovered a new type of cosmic alchemy. Here, this powerful flare resulted in a sudden production of a lot of heavier elements, which resulted in a lot of heavy atoms that were not stable. And these heavy radioactive nuclei decayed in mere seconds, producing much more stable elements such as gold. And it's really this sudden radioactive decay that we seem to be observing in that second emission. And that's because all of these elements would suddenly start to glow for a few seconds. In this case, this was visible as a sudden burst of gamma rays. And while based on total emissions, it looks like this produced approximately 1/3 of Earth's mass in heavy metals, or 1 Mars mass of gold, all resulting from things like iron that was suddenly enriched and became gold. And based on the amount of magnetars we expect and the amounts of flares we expect, this new research presents us with a new important explanation. This flaring process very likely produces up to about 10% of all heavy elements, potentially explaining where a lot of heavy elements came from and presenting us with another way heavy elements can easily form. But I guess more specifically, providing direct evidence that this is indeed possible, with the only other evidence we had previously being that kilonova from 2017. But in order to confirm this, we need to detect more gamma ray bursts and of course more flares from various magnetars. And so chances are that in the next few years, we'll actually discover more. And there's even a perfect telescope for the job. Compton Spectrometer and Imager that's going to be launched in 2027. A new gamma ray telescope that's going to be perfect in trying to detect as many of these as possible. But as of 2025, this is the only such detection. The only magnetar so far that was able to produce gold and of course other heavier elements. So today we're going to discuss a few more mysterious radio signals that as of today have no explanation. Radio signals that have been discovered in just the last few years and that currently just make no sense because of the way they're produced and because of certain parameters in them that current physics cannot explain. But specifically, we're going to delve into one of the most intriguing and rapidly evolving fields in astrophysics, the study of long period transients or LPTs, something that was only born a few years back and only as a result of new radio telescopes accidentally discovering these signals. And here we're talking about bizarre cosmic objects that present a significant mystery in how they generate these very powerful radio waves. And so in this video we're going to explore one of the most recent and I guess one of the most bizarre discoveries to date, the object scientists refer to as the unicorn, but also discuss some of the latest significant discoveries and examine how these findings help us learn about the universe and help us understand various radio signals coming from across the universe. But I guess let's start with the very important side note or clarification. None of this seems to be artificial or coming from some kind of an alien civilization, and all of this so far resembles natural signals we normally detect from things like pulsars. But the main reason these signals are mysterious is usually their length or their repetitive nature. But specifically, the actual mystery is in the name itself. They're called LPTs because they actually have very long periods that currently science just cannot explain. Usually in minutes, sometimes even in hours. But I guess let's discuss some of these new discoveries and talk about why this is important. And here we obviously have to start with the objects we do understand. Pulsars. Rotating neutron stars that emit very regular radio signals, but whose signals usually repeat with a frequency of milliseconds or sometimes tens of seconds, but never longer than that. And that's because based on modern physics and the understanding of how these signals are produced, which is actually the result of the rotation of the neutron star, it's actually believed that once these neutron stars start to spin much slower, they're going to become radio silent and produce nothing else. Which is why in our galaxy we seem to only see a few thousand pulsars and not billions, like we would expect if every single neutron star was emitting something. On top of this, we have another mystery referred to as FRBs, fast radio bursts. Very intense, short-lived radio signals, normally lasting just milliseconds, and normally only happening once. The first one was detected in 2007, and well, as of 2025, they actually still don't have a very good explanation. But now we have something that seems to be even more bizarre. A distinct class of radio signals characterized by ultra-long rotation periods, usually in minutes or in hours. And they were only discovered because a lot of radio telescopes were collecting so much data that it finally became much easier to see the bigger picture, where a lot of these signals were finally seen. And so unlike other radio signals, these unusual, sporadic and infrequent emissions don't really make a lot of sense and also present a challenge when trying to study them and when trying to detect them. And so when it comes to pinpointing the source of these radio signals, at the moment it's just impossible. Especially because a lot of them have been actually discovered deep within our galaxy and amidst a dense field of stars, making it very challenging to precisely determine what was generating these bizarre radio waves. But there was actually a relatively small breakthrough a few months back. We've discussed this in one of the previous videos in the description, but here a discovery of this particular object, which was obviously also an LPT, made it slightly easier to identify its nature. It was found on the outskirts of the Milky Way within the constellation of Puppis, and only approximately 5,000 light-years away from us, making this a relatively close radio signal compared to the ones discovered previously. And so even though the signal here repeated every 3 hours and lasted for anywhere from 30 to 60 seconds, which at that time made it the longest signal detected, by using the additional observations from the Meerkat radio telescope and the SOAR observatory in Chile, Associate Professor Natasha Hurley-Walker and the team from Australia was able to identify the spectrum of this object, discovering that it seemed to be some kind of a star, and specifically an M-type star, which we usually associate with red dwarfs. But this didn't make much sense because we don't expect any star to produce such an energetic emission, with the initial conclusion being that this must be a binary system, with very likely some kind of a white dwarf orbiting around a red dwarf, and the period in this case was very likely in their orbit. And so here's a suggestion: link this to a binary origin, similar to another system known as AR Scorpii, a known white dwarf red dwarf pulsar system that basically creates these emissions by doing what you see in this video. It excites the star by bombarding it with its powerful jets. But building on these initial discoveries, now researchers discovered something else really bizarre. An unusual cosmic object called CHIME J1634+44, although now simply referred to as the Unicorn. Mostly because of its very bizarre, very unusual and unexplained traits. Here this was achieved by using the Canadian Hydrogen Intensity Mapping Experiment and the Green Bank Telescope, as well as the Very Large Array and the NASA's X-ray Observatory known as SWIFT. And so why exactly is this called Unicorn, and what's so strange about this? Well, here the reason this kind of challenges current scientific understanding is because this is the only radio signal that seems to be spinning up. Or basically, its radio emissions seem to be getting shorter and shorter and shorter. Which is strange because normally, for a white dwarf or a neutron star, when they emit radio signals, they technically do the opposite. They slow down. And so this spin-up phenomenon strongly suggests that this object seems to be changing somehow and is very likely affected by something else in its orbit. So this is maybe also some kind of a binary object again. But if so, this has to be a binary system where the orbit is shrinking, because that's the only way we can explain why the emissions seem to be happening faster and faster. And the only way the orbit can shrink is through some kind of a gravitational wave interaction. And so here, if gravitational waves cause these objects to come closer and closer, this could potentially explain why the radio signals are happening faster and faster. But there is something else bizarre about these emissions, and something we've never seen before. Every single one of these signals is what's known as polarized, but specifically, it contains 100% circular polarization, meaning that every single radio wave coming from here has a perfectly spiral shape. And that's also never been seen before, especially with such consistency. No known neutron star, white dwarf, or really anything else has ever been observed to always exhibit the level of circular polarization observed with every radio burst. And that means that here, the mechanism producing these radio waves might be fundamentally different from anything we've seen so far in any other object. As a matter of fact, currently there is no way to explain why exactly this polarization even exists. And last but not least, there's also something else going on here. This object has a very complex periodicity. And complex because it seems to have at least two separate periods. The first one is roughly around 14 minutes long. So basically every 841 seconds, there is a radio signal coming from here. But there seems to be a second period of 4,206 seconds, which is precisely 5 times longer. And here we don't really know why, but I guess maybe there's also something else in orbit, or maybe this is some kind of a natural pulsation coming from inside this object. And so at the moment, this is probably the most mysterious radio signal we've seen in the last few years, and there's really no explanation for what's happening here, what sort of an object this is, and why we're seeing so many changes and so many periods, or so much bizarre polarization. So it definitely deserves that name of unicorn. But we can obviously make certain conclusions based on the observations. For example, when it comes to the polarization, this can only come from some kind of a magnetic environment around this object, suggesting a super complex magnetic field configuration never before seen in any object out there. And though examples of linear polarizations transforming into circular polarizations have been observed in other objects, such as the radio-emitting magnetar known as XTE J1810-197, in this particular case the polarization is not always so circular and does differ with time. But at least this definitely hints on this being the effect of the magnetic field and not something else we've never seen before. Likewise, when it comes to these changes or drifting elements, something very similar has been observed in fast radio bursts, suggesting some kind of a shared emission mechanism or some kind of a similar propagation effect. And since fast radio bursts have also been suggested to be caused by magnetars, here we have at least a few hints suggesting that this is maybe a magnetar as well. And so here, if this is a magnetar, it would essentially be a highly magnetized, very young neutron star containing extremely powerful electromagnetic fields in excess of what we usually observe around a typical pulsar. And so in this case, the explanation for these bizarre LPTs would be that this is a bunch of ultra-long period magnetars that just do something a little bit different from a typical fast radio burst or from a typical neutron star. But the overall question here is, so what do these signals tell us about various radio signals out there, and what do these discoveries mean for our understanding of radio signals and signals from pulsars? Well, first of all, this kind of expands our classification of these transients. This indeed seems to be a new type of a transient or a new type of a signal emitter that has never been seen before and seems to be caused by entirely different mechanisms. At the same time, this kind of challenges our existing models, especially because right now there is no explanation for how such compact objects can generate such extreme radio emissions. And though we have seen some other emitters, like for example rotating radio transients, that can generally produce emissions 1 second or longer, in this case LPTs can even last hours, which at the moment is somewhat impossible to explain. But when we try to compare these objects, there are still some unifying observations. For example, the fact that polarization in this case does suggest very strong, very unique magnetic fields that seem to be present around most of these objects. And at the same time, by discovering these exotic objects or these very bizarre, unexplainable phenomena, takes us just a little bit closer to understanding the entire universe. And while these findings may not have immediate implications, a lot of these scientific breakthroughs are going to become groundwork for future technological advancements and, of course, our understanding of everything around us, expanding humanity's knowledge base. And so by detecting these very sporadic distant signals, it pushes the boundaries of radio astronomy and international scientific collaboration. But just the fact that these objects even exist demonstrates the unexpected diversity of cosmological phenomena, reminding us of how much more there is to discover and how little we still understand about the cosmos. Hello wonderful person, this is Anton, and today we're going to discuss a discovery of a very strange pulsating object that currently does not make sense, and according to the researchers, should not actually be possible or exist at all. And that's because based on the observations and the recent discovery, this new object known as ASCAP J1839-0756 seems to be producing a lot of pulsating emissions we've never seen before and that cannot be explained using modern physics. And so let's discuss this unusual object in a little bit more detail, but I guess let's start with the discovery first. And while the first hint for the existence of this object was from the Australian radio telescope known as ASCAP, also known as Australian Square Kilometre Array Pathfinder. This telescope is actually known for producing the biggest radio map of the night skies we've ever had, and we'll discuss this in one of the previous videos in the description. And so during its normal operations and normal observations, there was one unusual signal that kind of stood out because there was really nothing around it. Here this appeared to be as an extremely strong radio signal that was at first getting brighter, but then started to dim, with its brightness going down by about 95% in just 15 minutes. And this was already kind of unusual and actually has not been seen before. For example, instead of a typical fast radio burst, this was actually an extremely slow radio burst. And so it wasn't clear exactly what happened here or what produced this emission. Overall, the emission looked something like this, which meant that additional observations would have to be required in order to find out what's up here. And that's exactly what the scientists recently did, in the process uncovering a lot more emissions, especially when combining this with several other telescopes, including the famous Meerkat from South Africa. And this time, instead of a single emission, they actually discovered that this is a periodic emission that happens extremely slowly, with the new data suggesting that it takes approximately 6.5 hours between pulses. Or basically that this is indeed a pulsating radio object, but with an extremely long period we've never seen before. And this is basically where it kind of makes no sense. And I guess let me explain why. Normally when it comes to pulsating radio sources, we usually detect them from various neutron stars, the most common one being a pulsar. And so typically what we actually see from pulsars is basically one of their beams pointed almost directly at us, with the periods corresponding to the wobble of the pulsar as it spins around its axis. And obviously in the last few decades, thousands and thousands of pulsars have been discovered pretty much everywhere, some of them spinning ridiculously fast, up to approximately 700 times per second, and you might actually want to check out one of the recent videos where another such pulsar potentially established a kind of a spinning limit when it comes to the maximum velocity. That video should be in the description below. And some pulsars spinning much slower. But to date, the record for the slowest spinning pulsar seems to be 23.5 seconds per rotation. This pulsar was discovered by the Chinese radio astronomers approximately 7 years ago. But in the last few years, researchers also started to discover unusual long-period radio pulsators, or radio transients as they're also known, which turn out to be some kind of a new class of objects where they basically still get to emit radio waves, but they're just doing so much slower. Here the period usually ranges between 18 minutes to maybe 54 minutes. So hundreds to thousands of times slower than a typical pulsar. And that actually did not make much sense, mostly because of how we think it works for a typical neutron star. In order for a pulsar to produce these radio pulsations, it has to actually spin pretty fast. And so in a typical pulsar, it's really the rotation of the magnetic field that has to happen really fast that produces these radio emissions. And that's because this magnetic field basically acts as a kind of a particle accelerator that accelerates various electrons that were produced as a result of gamma radiation coming from the neutron star interacting with the magnetic field around the pulsar. And so essentially through this rotational interaction of the magnetic field, a lot of these electrons are accelerated to very high velocities, which produces radio emissions in two separate directions following the magnetic field. But the object has to be spinning really fast for all of this to work. And so according to modern theories, it has to spin at least once per minute. Otherwise, it's actually going to stop producing radio waves because the magnetic field is just not going to be able to create any of this anymore. And so the previous detection of these long pulsators already produced a bit of a mystery. But here there might be one explanation. Maybe these are actually not pulsars, but possibly magnetars, which could be producing these emissions in some other way through a different mechanism involving a much more powerful magnetic field. Or alternatively, these could be highly magnetized white dwarfs, which would be spinning much slower and may have similar magnetic properties, allowing them to pulsate in a similar way. But so far, individual white dwarfs have never actually been found to have these unusual pulsations, or at least that was the explanation for previous detections of these long-period oscillators detected in the last few years. And here we're talking about pulsations in minutes. But now we have a different story. Here, whatever is pulsating is doing so every 6.5 hours. And that's completely unexplainable. This would be the slowest pulsar ever discovered, and a pulsar where the mechanism cannot be explained using any technique. For example, can this be a magnetar? Well, pulsating magnetars have been discovered before, and actually with even slow pulsations, but all those pulsations were in the X-rays, not in radio light. Here's actually one of these examples, the Magnetar 1E 161348-5055. That's technically a supernova remnant that produces periodic X-ray emissions every 6.6 hours. But here we see no X-rays, only radio light, which would make the magnetar explanation very challenging. Now, could this be some kind of a magnetized white dwarf? Well, usually white dwarfs produce other emissions as well, and in this case, no signs of white dwarfs have been seen so far, and no additional emissions or additional observations seem to be visible. Basically, no evidence for this being some kind of a white dwarf either. And so if not a magnetar, and if not a white dwarf, and if it cannot be a typical pulsar, what is this? What can possibly produce super strong radio emissions every 6.5 hours, yet produce no other emissions visible so far? And the answer is, I don't know, actually nobody does. This is basically a new, completely unexplainable, mysterious object. But what makes this object even more mysterious is the fact that even trying to model this or explain this physically just doesn't make sense. But we do have some hints based on what we know about pulsars and neutron stars. In other words, there's maybe a hint that this is a neutron star. And this is actually based on the orientation of the magnetic field compared to the rotational axis. So normally, in a typical pulsar, the rotational axis is just a little bit misaligned with the magnetic axis, which is actually one of the reasons pulsars can pulsate, beaming their light toward us. But in this case, for this pulsar, its magnetic axis seems to be almost at 90 degrees from the rotational axis, because during one of the observations, it was actually determined that it seems to produce a second flash after about 3.2 hours. This is known as the interpulse, and it's basically coming from the opposite direction, but it's not directly pointed at us, so it's much more difficult to see. And this apparently happens to approximately 3% of all pulsars we've seen so far, implying that this is maybe some kind of a really bizarre neutron star we've never seen before. But the problem is, of course, the fact that this spins so slow. All of the previous detections were spinning at least several times per second, and in every single case, over time as the pulsar slows down, we expect these radio emissions to stop completely. Nevertheless, there is still at least one hint right now that this is maybe a magnetically driven process from some kind of a very bizarre neutron star. Or, I guess, aliens. Well, maybe not aliens because the emissions here don't really seem to produce anything resembling artificial communication. Either way though, there is definitely a huge mystery now. The mystery of what exactly this is, how it works, or even how far away this object is from us. At this point, all of this is still unknown. Now, chances are if we actually discover similar objects somewhere out there, it will become much easier to explain them. But for now, many of these long-period pulsators discovered in the last 3 years don't really make a lot of sense. And though it was already difficult to explain pulsators with 50-minute periods, here we have to now explain one with 6.5-hour period. Which means that for the next few years, this is most likely going to be rewriting a lot of physics books, and may even end up producing some kind of a new model about neutron stars, or even discover some kind of a new object we never knew existed before. Maybe this is actually some kind of a bizarre quark star, or something else really exotic that we could not imagine before, but that was always right here, sending signals to us, just extremely slowly, so this is the first time we've detected it. And so at least for now, ASCAP J1839-0756 is going to become a new radio mystery, joining the ranks of FRBs and a few other emissions we've discussed in some of the previous videos that still cannot be explained. Hello info person, this is Anton, and today we're going to discuss a somewhat intriguing proposition when it comes to the idea known as the stellar engine. or essentially a hypothetical megastructure which would use the resources from a star to generate propulsion in order to move the entire star system. And though this idea has been discussed before, including in some of the videos right here on YouTube, today we're going to discuss one proposition that's actually just a little bit more intriguing because it does involve mysterious objects we refer to as black widows. And it also involves a new hypothesis in regards to extraterrestrial intelligence, referred to as the Stellivore hypothesis. Or basically a hypothesis in regards to advanced civilizations, where the civilization becomes so complex that it eventually starts to basically eat its own star. And the consumption of the star in this case is used for both energy and to potentially migrate to a new favorable location somewhere in the galaxy. Thus, Stellivore, Eater of Stars, which is actually based on the Dyson sphere hypothesis, but kinda takes it to a completely new level. And so let's discuss some of these recent studies and recent observations in a little bit more detail, but I guess first let's start with the theory behind black widows. Now you can actually learn about these objects in some of the previous videos in the description, but in a nutshell, in the last few decades, researchers discovered these unusual objects, which are in essence pulsars, but are just a little bit too extreme. An extreme in a sense that they're basically eating up their own partner, destroying it in the process. Which is why the first such object was actually called Black Widow. You can see this famous object right here. This is an actual image in the X-rays. And naturally, to explain this, researchers proposed that this had to be a binary system where a newly formed pulsar or a neutron star is very likely orbiting super close to its partner, possibly between 1 and 14 lunar distances, or basically just a few 100,000 kilometers away from each other, with the pulsar in this case producing so much radiation and so many pulsar winds that it basically starts evaporating its partner. And this evaporation can be visible from very far away, which is exactly what's visible in this image. And well, as of 2024, just over 40 such objects have been discovered, and they've now been classified as one of two potential types. They're essentially named after dangerous spiders, black widows and redbacks, with the main difference being their partner. All black widow pulsars seem to have a companion with less than 5% of the solar mass, whereas redback spiders have much larger partners, usually between 1/10 and 1/2 of the solar mass. And in the last few years, researchers actually discovered that, well, there seems to be a direct correlation between the mass of the partner and the energy produced. Redback spiders are usually much more luminous in the X-rays because they do have more massive companions. And in one of the previous studies, it's basically been explored and potentially explained as a result of various shockwaves interacting with the solar atmosphere, when various stellar winds strike the winds from the pulsar and create massive, really hot shockwaves, which are then visible in the X-rays. And this was actually directly observed inside one of the more famous globular clusters known as Omega Centauri. Each of the objects you see right here, visible in pink, these are basically spider pulsars, either black widows or redbacks. Surprisingly, there are 18 of them just in this cluster alone. And this will be actually important in just a few minutes. But generally, despite unusual features and despite unusual emissions, these objects have always been believed to be more or less well understood. We essentially believe that eventually this will completely evaporate the object, possibly turn it into some kind of a planet, or maybe even making it disappear almost completely. And previously these objects were probably much more massive as well. So this is definitely a long-term process. But there's always a possibility for some kind of a mystery or for something we don't understand. And specifically, when you actually look at their emissions, it really looks like they're basically little rockets or little comets, in essence moving in a single direction. And this is essentially where this new hypothesis kind of starts. A few years back, a Belgian scientist, Clement Vidal, proposed an idea known as Stellivore hypothesis. In essence, it was based on a simple premise. The premise that advanced civilizations might not just want to build some kind of a Dyson sphere, but instead might also completely consume their own star because of their energy requirements. And so in some of the previous papers, his goal was to basically determine what kind of technosignatures can we actually discover in order to see if this is actually going on. And in his hypothesis, he basically proposes that initially, these advanced civilizations would mostly consume the star via the process of accretion. But at some point, because the mass here is not unlimited, instead of consuming the star completely, this type of civilization might actually initiate its next phase. Now, it would use a low-mass companion star as a source of fuel and propulsion instead of a source of energy, and that's to basically reach a new location. Naturally, this could only be possible in a star system with at least 2 stars, so these would be civilizations inside binary star systems. And it just so happens that these black widows seem to fit the picture pretty well. So basically here we have these spider pulsars that no longer accrete material, but are actually evaporating the partner, which very likely produces propulsion in the process. And so here the thrust is generated by first being stripped from the companion and then accelerated away from the star system. And all of this is essentially driven by these really powerful pulsars. And so in the recent paper, the focus is on trying to explain how this propulsion could actually work, and how in theory it's possible to control the binary system and even its motion. So for example here, it becomes possible to move in a certain direction and to even steer in a certain direction by timing the radiation and the heating of the layers in the smaller partner with the emissions from the pulsar. And additional acceleration or deceleration could also be controlled with massive magnetic sails around the evaporating star. And so basically, by timing various emissions, in order to heat up layers around the star in a different way, it becomes possible to kind of guide it to a certain location, making this a type of a binary stellar engine. And so in essence, this recent study focuses on exploring this possibility and essentially tries to figure out if there are maybe certain technosignatures we can detect in order to confirm if this is really happening. And additionally, there is another assumption here. The assumption being that if this is true, these spider pulsars are headed somewhere. So they probably have some kind of a star they're trying to approach because that's where they're being guided. And so here, by focusing on some of the observations from the Gaia telescope, the main researcher tries to determine 3D motion of the entire system, eventually discovering that there is actually at least one star that might be its potential destination that is going to be reaching in approximately 420 years. But here there's definitely a lot of uncertainty when it comes to the motion, and so this is obviously open to interpretation. But this topic is actually explored in at least several studies, basically trying to figure out where these spider pulsars are headed. Right now there's no conclusive evidence for anything yet, but it is an intriguing proposition, with the study even going as far as to state that these are basically living binary systems. And so in essence we have our payload, which would be the pulsar with approximately 1.8 solar masses, and the propellant in this case is the companion star, usually up to about 0.7 solar masses in mass. And interestingly, we even get the efficiency calculations comparing this to other stellar engines, and as you can see from this table, the binary stellar engine is basically one of the best. And so the main question in the study is, of course, could this be real? Could these really be extraterrestrial intelligences using stars to move themselves to a different location? And well, there's really no answer in this paper, but this presents us with the best and possibly the easiest potential opportunity to try to detect technosignatures. Mostly because here it would be much easier visible, especially if we actually find evidence that something in this case seems to control the thrust of this object, moving it in a certain direction towards some kind of a star. And especially if we actually discover that many of them seem to have destinations, because that would be kind of difficult to explain. But right now these are just propositions, and there's just no evidence for anything yet. And so even though spider pulsars seem to present us with the best possible candidate for observing stellar engines, and we actually do have decades of data and a lot of different studies focusing on them already, since this is the first potential suggestion that this could be a Type 2 civilization basically moving around the galaxy, no actual observations of technosignatures have been done yet. Although here, I guess let's be a little bit critical as well, because in this particular case, it would be kind of difficult to explain why we actually see so many of them inside Omega Centauri. Here, a lot of stars are actually really close to each other, and moving from one star to another shouldn't really be that difficult, especially for a Type 2 civilization, yet for some reason we observe at least 18 known spider pulsars inside this dense region. And if these were basically stellar engines, it might be difficult to explain why. But if these are binary systems that naturally formed pulsars, where one of the pulsars just started to destroy a star, resulting in this, it would make just a little bit more sense. In other words, explaining this using a Type 2 civilization might actually be a little bit more challenging. But that's just, of course, my take on this. What do you think? Anyway, still a super cool proposition, and I think a really cool idea when it comes to a new type of a stellar engine and a new type of a potential civilization that could exist out there, but obviously still a hypothesis. We'll definitely discuss this in some of the future videos once there is maybe some updates or some new discoveries. Until then, check out additional videos on similar topics in the description below. Thank you for watching, subscribe, share this with someone who loves learning about space and sciences, come back tomorrow to learn something else. Support this channel on Patreon by joining channel membership or by buying the Wonderful Person t-shirt you can find in the description. Stay wonderful, I'll see you tomorrow, and as always, bye bye.